Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, and we are dealing with Chapter 4. I think my video I recorded before was 4.2, but if you're in sequence, we're in 4.1. You know what? You might want to do 4.2 beforehand. I don't know. Well, it depends on how your teacher's working it out, but 4.2 was solving by graphing, and we just came off of graphing. So 4.1 actually leads better into 4.3. So 4.1 is this video here, properties of radicals. I think that's what it's called, properties of radicals. And this really leads into 4.3, 4.4, 4.5, where we start solving equations using these other methods, square roots, completing the square, quadratic formula. Because all of them require doing a square root of something at some point, and you have to simplify those radicals within. Not in all of the different veins that you're going to see in this video. In fact, this video covers a lot of different things that lead well into IM2 material and whatever. It's pretty good stuff. It covers a lot, and it can go pretty fast, you know, if I use like more choice words and try and figure out, you know, how to teach it to you the best. And if I see some patterns, I'm really going to drill and kill it, because guess what? We have 107 problems to do. It's quite a bit, and I don't know how much memory I have on my computer. I could probably only go 3 hours worth, and I'd love to do a lot less than that if I can. So I'm going to dive through the lecture, see how they talk about it, see how I say things in comparison to it. Let's go ahead and check it out. Use properties of radicals to simplify expressions. Simplify expressions by rationalizing the denominator, that's a phrase, and perform operations with radicals. That means add, subtract, multiply, and divide. But rationalizing the denominator is going to be a key thing later here. Let's see some of the core vocab. Counterexample. I actually don't know how they're going to use that. Radical, by the way, is like this square root thing. It's not always square roots, though. It could be cube roots, could be fourth roots, whatever. But that symbol. Simplest form of radical. Excuse me, breaking them down. That's what we're trying to do. Rationalize the denominator. We'll get to that. Conjugates is what we're going to use to rationalize the denominator quite a bit. Like radicals, kind of like terms. Okay, perfect cubes, perfect squares, perfect fourth power, the cortex, things like that I can say. A radical expression is an expression that contains a radical. Once again, one of these symbols here. An expression involving a radical with index n. I sometimes just call it root, but index is referring to this guy right here. Index n is in simplest form when these three conditions are met. This is interesting. Let's see. No radicands. I think that's things inside the radical. I don't even know all the terms. No radicands have perfect nth powers as factors other than 1. No radicands contain fractions. No radicals appear in the denominator of the fraction. Yes, perfect. Okay, so we simplify a radical by satisfying all three of these things right here. And I don't know if I want to give examples before I show examples, meaning I'm not going to give my own. So let's see how these conditions are met when they talk about these three things. Because maybe you're like, I don't get it. We're going to get it together. What you do need to know, though, are perfect nth powers. I don't mean you need to know what they mean. You need to know what they are. And they're saying other than 1, which is important. For example, perfect squares, and you should know these from quadratics, are like 4, 9, 16, 25, 36, 49. These are perfect squares. Perfect cubes, 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, like those. We're going to have to know those. I'll call them out, and you'll just have to agree and accept, use your calculator. And there are lists you can find online somewhere, I'm sure. You can use the property below to simplify radical expressions using square roots. So here's what they're showing. Algebraically, I'm going to point to first. The square root of a product equals the product of two square roots. You can split up anything that's multiplied into two different square roots and multiply them. You can do that for multiplication, and I'm sure they'll show it. You can use it for division. You cannot do it for addition and subtraction. Here's an example, and I want to show it even before this because they're showing root 9 times 5. The square root of 45 can be broken up into root 9 times root 5. And we do that so we can take the square root of 9, which is 3. This is an example of simplifying a radical. What are we doing? We're taking out a perfect nth power as a factor. In other words, 9 is a perfect square. We have to factor it out of the radicand. I say inside the square root. You have to factor it out of the square root. We take its square root. 3 root 5 is equivalent to the square root of 45. This is how we call it, 3 times the square root of 5. It is equivalent, but it is known as, it's simplified. It's known to be simplified. And that's what we're doing with that one. So here's some other examples. 108. And your goal, by the way, I'm always going to do this. I'm not going to lead you astray. I can show you instances, I suppose, but I don't want to. Your goal is to find the largest perfect square possible that can factor out. So 36 is 6 squared, right? It's the largest perfect square you can factor out. And you'll know it's the largest perfect square because this number, not necessarily always a prime number, but it won't have any other perfect square factors that exist inside of it. Because if I factored out 4 out of here, you'd have root 4 times root 27. And 27 still is a perfect factor of 9, perfect square factor of 9. Anyway, square root of 36 is 6, and you're left with 6 root 3, which is equivalent to the square root of 108. They're both 10 point something, probably close to 10.4 or something like that. Now, this is also true with variables. 9x cubed, the square root of 9x cubed. You can treat numbers with numbers, variables with variables. So the square root of 9 is 3 straight up, but the square root of x cubed, look how they break it up. They do the square root of x squared times x. They take something where, and we've done, I think, we've done square roots of, right? I think so. We've done square roots of variables where we divide it by 2. The square root of x squared is also x to the 2 over 2 power, which is x to the first. That means this comes out. This is a perfect square of x. So that came out, and this x stayed on the inside. It is not a perfect square, just like 3 is not a perfect square, and it stays inside the radical. There are more here, but we are going to do our own. Let's take a look at the next one, and this is the one I was mentioning. Quotient property of square roots. The square root of a quotient equals the quotient of the square roots of the numerator and denominator, so we can take something that is divided and split it up into their own 2 separate parts. And that's ideal because we cannot have a fraction inside of a radical, like they said. And furthermore, which we're going to get into, you can't have a radical inside the denominator either. Thankfully, 4 is a perfect square. The square root of 4 is 2. So root 3/4 becomes root 3 over 2. You do need whole numbers in the denominator. That's going to kind of be a thing. So algebraically, it looks like that, splitting up into 2 things there. Okay. So here are some examples. Root 15 over 64. And by the way, if you can reduce the fraction beforehand, go ahead and do it. This one cannot reduce. Square root of 64 is 8. The square root of 15 cannot break apart more because even though it's a composite number, it doesn't have any perfect square factors inside of it. So you get root 15 all over 8. Root 81 over x squared, you take the square roots of them separately. And by the way, you don't have to write this step if you know what's going on from one to the next. Say square root of this over square root of that. So it becomes 9 over x, and all's good. Okay, you can extend this to other radicals such as cube roots or fourth roots or whatever. It doesn't have to just be square roots, but you do need to find perfect cubes and stuff now, not perfect squares. And they do mention that cube roots can have negative numbers because when you cube a negative number, it becomes negative, so you can take the cube root of a negative, whereas you cannot take the square root of a negative. So the cube root of negative 128 is totally cool. You're going to get a negative value out. We have to find a perfect cube. 64 is a perfect cube as it is a perfect square, or negative 64 in this case. And the cube root of negative 64 is negative 4. So you have negative 4 times the cube root of 2, as 64 times 2 is 128, and 2 is not a perfect cube. 125 is a perfect cube of 5, so that'll completely come out here. X to the 7th, you try and find, basically, you pull out as many x's as you can with a number that's divisible by 3, in this case, 6. 7's not, so we get 6 with a remainder of 1. We get to take the cube root of 6. 6 over 3 is 2 there, and the cube root of x stays within. And this last one, the cube root of y over 216, you split them up into 2 separate things. Cube root of y, not a perfect cube, so it stays inside there. And the cube root of 216 is 6. One of those things that either you're going to have to know or just trust me with when I tell you. Last one here, cube root of 8x to the 4th over 27y cubed. Again, treat numbers with numbers, variables with x's with x's, y's with y's, that kind of thing. Cube root of 8 is exactly 2. Cube root of 27 is exactly 3. Cube root of x to the 4th, let's break that up into x cubed times x. So we get to, like, the way I'm going to say it is basically what's 4 divided by 3. Excuse me, 3 goes into 4 how many times? I'll say it goes into it once. That's what this one comes out with a remainder of 1. And that's what's going to happen there. In the denominator, y cubed is a perfect cube of y. So this is what's remaining there. And they do more simplification practice on those ones. We keep moving forward. Let me take care of some sniffles. Okay, sorry if I sound a little congested. It's been a while. It's just allergies. Okay, here's this phrase called rationalizing the denominator. Now, what you've noticed is the previous problems had perfect squares, perfect cubes, and stuff inside the denominator. We were all taken care of. But what if you can't? We have the square root of 5 over the square root of 3n. 3 is not a perfect square. N's not a perfect square. There's nothing here. Do I just leave it like this? No, you cannot have a radical inside the denominator. The basic goal is you have to have whole numbers. Now, your value, your overall value may be irrational, which is fine. The denominator just can't be irrational. So here's what you do. You multiply the fraction by an appropriate form of 1 to eliminate the radical from the denominator. This is perfect how they mentioned 1. Remember, we can't change our value. Whatever root 5 over 3 root 3n is, it needs to stay as root 5 over root 3n value-wise. Like, just ignore the n for a second. Root 5 over root 3 is some value. Our final answer, this root 15 over 3, still needs to be the same value. And it is. But we can't have an irrational denominator. So we multiply it by 1. But our form of multiplying it by 1 is multiplying by the same thing on top and bottom. Any non-zero number divided by itself is 1. Now, what do we want to multiply by? In the case of a single term radical here, you want to multiply by the same exact thing. Because multiplying something to itself ends up canceling the the radical. You have like square root of a times square root of a equals a. That's my shorthand way of showing that. Multiplying something to itself exactly in a single term process. They'll show you by actually doing 3 times 3 is 9, n times n is n squared. You know what the square root of 9n squared is? Square root of 9 is 3, square root of n squared is n. So root 3n times root 3n is 3n. Now on top, you end up kind of working what's inside. Root 5 times root 3n, you can multiply radicals back together. We talked about splitting them apart. You can fuse them right back together as well. Root 5 times root 3 is root 15, and times the n is root 15n. So we get root 15n over 3n, and now things inside of a radical cannot divide with things outside of a radical. So it's not like you turn this into 5, no. Or cancel out the n's, no, because one's inside a radical, one's not. So square roots can multiply with square roots, cube roots with cube roots, irrationals with irrationals, like that. That's how it works. Okay, this one here, and they're getting a little particular with it, and I'll try and work it similar-esque, but I want to really talk about it however it is. You need to find a perfect cube. Cube root of 9, I can't just multiply it again by the cube root of 9. I need to multiply it by something to give myself a perfect cube. So find the smallest perfect cube that you can out of this. 9 times 3 would give you 27. So that can work. Multiply by cube root of 3. There are other ways I may refer to it if it's more difficult or if it's less obvious. But I think that's straightforward. Maybe just find the smallest perfect cube. I don't even know if I ever thought about talking about it that way. I would have brought it up in a different way to my own students, but actually this actually works out. But you have to know your perfect cubes. 9 times 3 is 27. Cube root of 27 is 3. But you got to multiply 2 by the cube root of 3, and that remains on top like that. 2 times cube root of 3, all over 3. So the next type of rationalizing denominator, you notice this 2 minus square root of 3. You can't just multiply by root 3, You can't just multiply by root 3 over root 3 because this would distribute into both of these terms. And although root 3 times root 3 is 3, 2 times root 3 does not rationalize. It stays irrational. Okay, so you can't just multiply by that single thing. Then you're probably thinking, okay, well, before we multiply by the same thing, let's multiply by the same thing here. Well, no, we've learned what squaring something does. Multiplying something to itself. It becomes a perfect square trinomial of a squared minus 2ab plus b squared, or whatever, plus that, and you still have this. So that doesn't work. So what do you multiply by? You multiply by what's called the conjugate. You see this a root b plus c root d. That's a lot. That's a mouthful. But when you have something as much as this amount here, and you can multiply it by what's called its conjugate. The conjugate is where you change one of the signs of the other things, because it cleans it up. They're actually showing this on the side to you right now. What happens is you create a difference of two squares. This is like an a plus b times a minus b becomes a squared minus b squared, that kind of thing. What ends up happening is the middle terms cancel, the ones that still have rationals. Everything else multiplies to itself, and when you have square roots times square roots of themselves, they end up canceling out the square root. So you end up having no radicals in the end in that situation. It can get messy, it can get clean, it depends. We have numbers that are pretty clean overall. You're going to see how these things work. And after that, it just becomes reducing fractions how you need to. And that's where I'm not going to try and spend a long time talking about things. I hope that we can just hear it, accept it, and move on. I'm more about the simplifying part, not the reducing fractions part. I will be reducing fractions, but I want to make sure I explain it away and keep going. So let's see. 7 over 2 minus root 3. Get rid of the radical here by multiplying 2 minus root 3 by the conjugate, 2 plus root 3. 2 minus root 3 times 2 plus root 3 gives you that, once again, a minus b times a plus b setup, which becomes a squared minus b squared. That's the setup, difference of two squares. We learned that in chapter 2, I think. Chapter 2. 2.3 to be specific. So it becomes 2 squared minus root 3 squared. Now 2 squared is 4. Root 3 squared is 3, and 4 minus 3 is 1. Now on top, you have 7 distributing into both of those. It actually shows right here. 7 times 2 is 14, 7 times root 3 is 7 root 3, and 14 plus 7 root 3 over 1 is 14 plus 7 root 3. So this is equivalent to this. These are the same value. They just wrote it in a different manner, one where there's no irrational values in the denominator. In fact, there is no denominator. It's divided by 1. So it cleans up here. So they have more practice stuff. Once again, we have 100 some odd problems to be able to do ourselves. I'm sure we have more than enough. Okay, they have some real life problems. Check it out. The distance in miles you can see to the horizon with your eye level, h feet above water, is given that by this formula. Who knew? I really want to see if that's true. So if you're, however far you are above water shows how far in the horizon you can see. It's actually kind of cool. I wonder how they figured that out. How far can you see when your eye level is 5 feet above the water? So she's 5 feet above the water. You just substitute 5 into there. I don't even know if you have to, oh, you have to simplify here. I was going to say, I don't even know what this has to do with the problems. So they give you a model. And check this out, by the way. It's an entire square root here. So whether you rationalize earlier or after you substitute, it's up to you. But 3 times 5 is 15. You split it up into 2 radicals. And we want to listen, it's a word problem. I'm generally a fan on word problems and getting like the decimal answer thing. I don't want to say things like this. I know exact is something, but decimal approximation kind of makes more sense for context. For simplifying purposes, I'll do that. But we rationalize the denominator by multiplying top and bottom by whatever that denominator is, root 2. You get root 30 over 2. Root 30 can't simplify, so you get just root 30 over 2. About 2.74 miles. Who knew? Who knew with you think? Example 7. Modeling with mathematics. Ooh, the golden rectangle. I'm not going to talk about that right now, but maybe we get into golden rectangle later, or the golden ratio. The ratio of the length to the width of the golden rectangle is 1 plus root 5 to 2. The dimensions of the face of the Parthenon in Greece form a golden rectangle. What is the height of the Parthenon? So, a ratio also means division, like a fraction, so they write it this way. If the length to the width is 1 plus root 5 to 2, and they have the length as 31, that's equivalent to the 1 plus root 5. So setting up a proportion, the length to width equals length to width, or I guess they say height in this case. So we can cross multiply, which is what they do here, h times this guy, and 2 times 31. Then you solve for h, multiply both sides by 1 plus root 5. As far as rationalizing the denominator, you would multiply both sides by the conjugate, or both top and bottom by the conjugate, 1 minus root 5. You get 1 squared, 1, minus root 5 squared, 5. 1 minus 5 is negative 4. Now, personally, I'm not a fan of what they have as an answer. I know they're going to use the calculator, but if they're going to use the calculator, then they might as well use it here. I want to get a better exact answer. No negatives in the denominator either, actually. So you factor that out, kind of bring it up top and distribute. I would actually get 62 root 5 minus 62 all over 4 as a better exact answer. I'd say the book should be better about that. It approximately 19.16 meters, about 19 meters. Great. Okay, I believe that'll probably be the end of that. No, it is not. Oh, that's right. We have to do some operations. So here's the thing. We want to find like terms. Think of like x's and y's. Take a look at this problem. We have 5 root 7 plus root 11 plus or minus 8 root 7. Kind of treat it like 5x plus y minus 8x. The reason I call these ones x's is they both share that root 7. You combine like terms. 5x minus 8x is negative 3x. 5 root 7 minus 8 root 7 is negative 3 root 7. They even show it as root 7 being factored out, so you can do 5 minus 8. It's a like terms thing. I'm not ever going to write it like that. I'm just going to say find like terms. So we do not combine it with the root 11, just like I mentioned before. Root a plus root b does not equal root a plus b. You cannot put them inside the same radical like you can products. They do not operate the same like that. It doesn't work that way. So it stays simplified like that. Ultimately, you combine anything that you can. The thing is, though, we don't always treat them like x and y, because you look at something like part B. Okay, I can't combine 10 root 5 plus root 20, but I can simplify the square root of 20, because 20 has a perfect square factor of 4. And root 4 times root 5 is 2 root 5, and guess what? Now they're the same. Now I can do my 10x plus 2x is 12x thing. 10 root 5 plus 2 root 5 is 12 root 5. They do combine. Same thing here works for cube roots. 6 times cube root of x plus 2 times cube root of x is 8 plus times cube root of x. I'm sure they could have worked more fanciful than that, and I'm sure they will in our problems here. Multiplying radicals. Multiplying works as they did before. We can distribute. root 5 times root 3, root 5 times root 75. Now, there are a lot of ways we can go about doing this, and I don't know which one's better or worse. I've talked about it in past videos, but something like, listen, we're going to have to simplify things later, like root 375, which is pretty big. Apparently, it's 25 times 15. Wait, did I say that right? I think so. Root 25 times, yes. So root 25 times root 15 is 5 root 15. And then 1 root 15 minus 5 root 15 is negative 4 root 15. However, I also could have simplified the root 75 earlier. That was root 25 times root 3, so it's 5 root 3. I could have done root 3 minus 5 root 3 well before I ever... you know what? They're showing that right here. I'm sorry. I totally didn't see this. Method 2. They could have simplified root 75 to 5 root 3 beforehand, combined these, or even if they couldn't, you could distribute later and have smaller numbers. And then if there's something to still simplify, go ahead and do it. But now root 5 times negative 4 root 3 itself is negative 4 root 15. You still get the same answer. So simplify early, simplify later. It's up to you how big you want the numbers to get. I like to make them smaller first, personally. You just got to remember to simplify a second time if we have to. Okay, now we move on to the problem set, which is fantastic because that was a pretty long lecture here. The process of eliminating a radical from the denominator of a radical expression is called rationalizing the denominator. Rationalizing the denominator. Now, that name makes a lot of sense because we have to make a rational number out of it. Irrational numbers are ones that the radicals and stuff. We have to make it rational. What is the conjugate of the binomial root 6 plus 4? It's root 6 minus 4. This is the one that when you multiply one by the other, create a difference of 2 squares. No more radicals. Radicals be gone. Are the expressions 1 third root 2x and root 2x over 9 equivalent? Explain your reasoning. Well, I'm going to look more at this one and try and simplify it. Root 2x over 9. That's root 2x over root 9, which is root 2x over 3, which dividing by 3 is also multiplying by 1 third. So 1 third of root 2x, that is indeed the same, yes. I explained through math, I simplified it. And number 4, which doesn't belong, so basically I'm sure which one's different than the other ones. I'm not sure, a couple of these are different. So imagine this is a, negative 1 third root 6, and this is 6 root 3, 6 root 3. I assume it's just ones that these ones could combine together because they have root 3s as the same factor that exists. So if I wanted to add these, I could. So I'm going to say this one's different for that reason. Not about being negative or positive or something you could simplify or not. I'm going to say these ones are the same and that one's different. Different radical. Different radical. Not alike. How do they call it? Like radicals? Let me go back. Like radicals. They were unlike radicals in this case here, and that's what we're looking at. Okay, so you can see how I kind of talk a mouthful through some problems when they go a little bit faster, and I want you to be aware of that, guys. I have over 100 problems to do now. Okay, I'm going to take a hit of water. I want you to soak that in. There will be some drill and kill involved after I've explained something more than once, and at that point I'm then maybe just doing the problem. And there might be some parts I still have to simplify when it comes to working out the reducing fractions and making something exact. And it seems like we have to calculate some stuff here and there. So, guys, I'm going to go ahead and jump into it. Let's start. We have number 5 of the square root of 19. Oh, what are they asking us to do? Determine whether the expression is in simplest form. If it's not in simplest form, explain why. This is in simplest form. Now, it sounds like they're not asking us to actually simplify it. If it is, I'm sure we simplify later. This is simplest form. Here's the concept. 19 is not only doesn't have any perfect square numbers factors, but it's a prime number. It just, well, I don't know which way I should say it. It's not only a prime number, it doesn't have any perfect square factors in it. If I'm taking a square root of something, I need to find perfect square factors of it. That's not the case here. Number 6, we got the square root of 1/7. Square root of 1/7 is not in simplest form. It's not. I'm just going to say not. Reason. Fraction inside denominator. Sounds like we're not actually simplifying it though, but fraction inside, inside radical. Fraction inside your radical. Fraction, I don't know. They call it the radicand. Maybe I'm not using the right phrase. The radicand is a fraction. That's how I want to say it. I didn't. That's how I want to say it. Square root of 48. Not Not simplest form. It contains a perfect square factor. Contains perfect square factor. Perfect square factor. I'm going to use PSF next time. Not SPF, but PSF. Of 16. 16 is the largest perfect square that you can divide out. I'm not saying the largest number. 48 is the largest number you can divide out. Or 24 divided by 2. But 16 is the largest perfect square factor that can divide out. I can take the square root of 16, get 4, that kind of thing. Number 8, square root of 34. That is simplest form. Square root of 34, simplest form. I don't have to explain why, but there's no perfect square factor that exists. Listen, I know it's 17 times 2. 17 is a prime number. It's not a perfect square. Neither is 2. Some of your teachers might teach you how to simplify things using what's called prime factorization. I'm not in the camp of doing that right now. It takes too long. I mean, seriously, I work toward efficiency. It takes too long. I'm not saying teachers shouldn't teach you it. I'm saying that if they do, I'm not talking about it, and the book's not. But if you learn prime factorization, there are some good things to know about it. For example, root A times root A is A. That's a big portion of what you want to talk about. And we need to know that. But so just be aware about that. There's a big thing there. This is not in simplest form. Denominator is irrational. Denominator is irrational. Number 10. Number 10 looks good. Number 10 looks like simplest form here. That is 3 root 10 over 4. I'm looking for a few things. I'm looking for the denominator being a nice whole number, which it is. I'm looking for this radical not having any perfect square factors, which it doesn't. And I'm looking whether 3/4 can reduce, which it cannot. But so that is simplest form. Number 11. Oh, not even close. Once again, irrational denominator. We'd have to rationalize it. I'd multiply. You know what? Multiplying by the conjugate wouldn't even actually work here because it's cube root. I actually would be hard pressed to think about how I'd go about doing that. I think it would just take some time. You have to rationalize a couple. You have to do a couple conjugates, I think, to get the final result working. I actually don't know if that would work. I have to think about that. Anyway, yeah, I think you have to multiply conjugates just a couple times there. But anyway, not because you have an irrational denominator. I should probably type this out. Number 12. Thankfully, the problems are going fast enough, right? Here's the thing. I'm blessed that I don't think I'm graphing at all. Graphing sometimes just takes too long. It just does. There's a lot to do on a problem. 6 minus cube root of 54. If 54 is a perfect square factor, which it does, 27. 27 perfect cube factor, PCF. So not for that reason. If you can do that, you go ahead and do that, and you take it out. You take its cube root. Okay, now we begin simplifying, and we start with square roots. Variables can be included, and it looks like we'll have to prepare ourselves for that. Number 13, square root of 20. And like I said, after this section, after we learn kind of the process of how we break some things up, I'm going to go faster with things like this. So anytime I have a square root of 20 later, I'm going to say what the answer is straight up. Okay? Or just the process in between. Because right now I'm going to break this up into square root of 4 times square root of 5. Which, and normally I don't write sideways. I apologize on this. I think I'm going to waste too much paper going downward though. This becomes 2 times the square root of 5. 4 is the largest perfect square factor that exists inside of that square root. And break it down from there. These are equivalent. Number 14, square root of 32. I wonder if they're going to trick us if something's not reducible, but I'll tell you if they do. Square root of 32. 4 can factor out, but a bigger one can, which is 16. Square root of 16 times square root of 2. We take the square root of 16, which is 4. And we get 4 root 2. Equivalent to square root of 32. Number 15, square root of 128. By the way, and I don't know when I want to show this. Okay, I know when I want to show it. Okay, never mind. I'll tell you in a second. Square root of 128 is square root of 64 times square root of 2. 64 is a perfect square of 8. It's the largest perfect square that can pull out. We get 8 root 2. And I want to remind you, how do I know that I have the largest perfect square? This doesn't have to be a prime number, but this number has to not have perfect square factors in it, which 2 does not. So you're looking for the largest perfect square factor, so you do it in one shot. Number 16. the opposite of the square root of 72. Now, we're not taking the square root of the negative. We're taking the opposite of the square root, which is fine. It just means the answer is negative itself. If there was a negative inside, we can't simplify that in a real number sense. We'd have to use something else. Anyway, 72 is 36 times 2. 36 being the square root, 36 being a perfect square of 6. So we get negative 6 root 2. I really don't want to be congested anymore. Number 17. I might take a Benadryl timeout once I hit the word problems or something. Square root of 125b. So here's where the variables come into play. Again, we treat them separate. Before I even talk about the numbers themselves, let's just separate into those two things. Square root of b is not going to get out of here. It's not a perfect square. Root 125 itself is not a perfect square, but it does have a perfect square factor of 25. So I can take root 25 times root 5 times b. Square root of 25 is 5, so you get 5 root. And you know what? I don't think I mentioned this before. When you simplify something in the end, you do bring anything back together inside of the radical when all said and done. So I don't leave it as root 5 root b. I leave it as root 5b. If anything couldn't come out, you bring it back inside one radical hat. I should only have one square root in my answer ultimately if it's just multiplying things in a single term. So 5 root 5b. It never left. Number 18 is where I'm going to bring something up here, for example. Root 4, and I don't think people would do it as much with the number 4, but square root of 4x squared. Split it up, square root of 4 times square root of x squared, all great. Now here's the thing. You get so hung up in this simplifying process that you start seeking perfect square factors that sometimes you forget when numbers are perfect squares themselves. Now 4, like I said, is a relatively small number. I'm sure you'll be fine with it. But you start trying to break it up, you're like, oh, I can't break it up into perfect square factors. Something like that sometimes happens when you forget the number itself is just a perfect square. But not only that, here's what I also get a lot of. And there are things that I also get a lot of over here that I'll mention as well. Square root of 4, a lot of people will put this, 2 root 2. No. Square root of 4 isn't 2 root 2. The square root of 4 is 2. It's root 2 times root 2, if you want to put that. And root 2 times root 2 is root 4, which is 2. No, it's just 2. So remember how to take the square root of a perfect square. We're doing it right here, right? But here's what some people also do. Remember this root 25? Some people turn it into root 5, meaning you leave the square root there after you've taken the square root. Listen, and these are weird statements that I'm going to mention right here. You don't get rid of the square root until you take the square root of something. And I bring that up in the case of, I'm sorry, I paused on this problem. I understand it. Let's look at the root 72 again. You know what I get a lot of answers of? 36 root 2. Okay? How did this leave a square root? Why is 36 not inside a square root? I never took the square root of anything, right? So you don't get rid of the square root of the radical until you take the square root of something, number 1. And number 2, when you take the square root of something, you get rid of the square root. This doesn't turn into root 6. It turns into 6. Root 36 and root 6 are two completely different numbers. Root 36 and 6 are the exact same number. Anyway, let's move on to this. Root 4 is 2. That's really what I want to tell you. It's not root 2. It's not 2 root 2. It's not square rootable. And the square root of x squared is x. That's a perfect square root of itself. That is the answer. You're like, man, you spent a long time explaining number 18. I wasn't explaining 18. I'm explaining misconceptions on these things because it's great for me to tell you what to do. I'm not telling you what to avoid. And I really should. Because, man, do I see it a lot. I'm going to see it from my students. You're going to do it. Not all of you, but some of you out there. Your teacher's going to talk about it and all that. Okay, negative square root of 81 m cubed. Okay, negatives on the outside. Great. We got square root of 81 and square root of m cubed. Now, the square root of 81 is 9. So, we have negative 9 outside. And here's this part, right? What you often saw in the book, in the examples, was this, breaking it up into two different parts. M cubed is m squared times m. And what I did was I chose 3 can't divide evenly by 2, but 2 can. So you find the largest value that can divide by 2, and you leave anything else inside the radical. Totally cool. Square root of m squared is m, so you're left with negative 9m times the square root of m. Negative 9m root m. And I'll stay on this one for this last question here, number 20. Root 48n to the 5th. And like I said, I'll be faster on these for other problems like this when we hit them. If I'm like rationalizing denominator, I'm sure the next set I can do it as well. This is root 48 times root n to the 5th. The square root of 48 can be broken up into the square root of 16 times square root of 3. Now here's where that root n to the 5th, break it up as root n to the 4th times root n. I want to divide 5 by 2. Remember, square root means second root there. And we can divide 4 by 2, but not 5 by 2, right? 5 divided by 2 is 4 divided by 2 with a remainder of 1. Anyway, square root of 16 is 4 times root 3 times square root of n to the 4th is n squared. Not because it's the square root of 4, because it's 4 divided by 2 times the square root of n. So what we do is we kind of bring all these together. 4n squared stay on the outside together, and root 3n stay on the inside together like that. Maybe that's more work than I needed to write, but ultimately that's where we get. There we go. Okay, 15 minutes for 15 problems, or something like that. So not too bad. It looks like we can go okay, but I'm sure they get longer as we keep moseying along. Okay, simplify the expression. Oh, give me 1 second. Give me 1 second. Okay, sorry, I just got a text. Okay. I don't know what I was talking about, but it looks like we're going to the next set of problems. So number 21 to 28, simplify the expression. So now we have some things that are fractions. Now we can't end up having a fraction inside the denominator, which is exactly what we're looking at here. Root 4 over 49 is the square root of 4 over square root of 49. This is why can't have a radical inside the denominator like that. So can't have a square root of a fraction because of this reason. Anyway, these are still perfect squares. Square root of 4 is 2. Square root of 49 is 7. You get 2 7s. And I'm set. We have number 22, where we have, and I think all these are perfect squares to start. I don't think we're rationalizing denominators yet. Excuse me. So negative square root of 7 over 81, which is negative square root of 7 over square root of 81. Square root of 7 cannot simplify or break down further, but the square root of 81 is 9. And a weird looking 9 at that. Negative root 7 over 9. Number 23. Sorry, I have a lot of things I have to control. Negative, I wish someone could be at the controls for me on one part of the screen, or I wish I could edit it so that it didn't do that. Negative square root of 23 over 64. Once again, we're taking square root of top and bottom, and I think at some point I'll probably, again, after this set of problems, I'll probably stop writing the in-between step of splitting it, and you'll just understand that they're being split. 23 is a prime number, cannot simplify any further at all. Square root of 64 is 8, and we're left with negative root 23 over 8. Number 24. Root 65 over 121. I mean, these are pretty consistent pattern, and I think sometimes the odd and the even are the same kind of problem. So like this one, root 65, can't break it down more. Listen, it's a composite number, but 65 is 5 times, I think 13. Or 13 times, yeah, 13 times 5. So, it doesn't, no perfect square factors with that. Just root 65 straight up. But root 121 is 11. So you got root 65 over 11. 25. Square root of a cubed, oh, now we're talking. Square root of a cubed over 49. Now, this is the square root of a cubed over square root of 49. Square root of 49 is 7. Let's get that one taken care of first. Square root of a cubed, we can simplify. It has a perfect square factor of a squared. I'm going to start talking about it the other way that I generally do. 2, remember this is an invisible 2. 2 goes into 3 once, so there's a to the first outside of here with the remainder of 1. 3 divided by 2 is 1, remainder 1, right? That's what's happening there. So a times the cube root of a all over 7. Or a squared times a, and you take the square root of the a squared. Because that's what we do with the numbers, right? Which we're probably going to be doing pretty soon here. Number 26. Number 26. Square root of 100. Whoops. Square root of 144 over k squared. That's the square root of 144 over square root of k squared. The square root of 144 is 12, and the square root of k squared is k. You are left with 12 over k. You can have variables inside the denominator as long as they are rational. Number 27. I'll leave some of that up there so you can see it in case I'm going way too fast. You have the square root of 100 excuse me, over 4x squared. So listen, this has a couple things here. It has square root of 100 over square root of 4 times square root of x squared. You can split up products inside of that part as well, right? It's not just only in products and only in quotients. It's quotients with products. Square root of 100 is 10, square root of 4 is 2, square root of x squared is x. Now I'm not done in this case because 10 divided by 2 can become 5. 5 being in the numerator, x being in the denominator. Now that's one method of doing this problem. If you didn't notice before though, 100 over 4 could have divided prior to this. So I could have had 100 over 4 inside that same radical being 25 to begin with, and 25 over either this way or this way, 25 over x squared being now root 25 over root x squared, which becomes your 5 over x. So more than one way of doing that. If you want to simplify something earlier and reduce it earlier, go ahead. Now it depends on what you're dealing with. Because look, let's put it this way. Let's say I had root 2 over 4. If I turn this into root 1/2, then suddenly I have to rationalize my denominator. But if I get to take the square root of 4 and call it 2, then I'm already taken care of. So I might not want to reduce something from a perfect square if it omits a perfect square. But 100 over 4 is 25 over 1, and 1 is still a perfect square, so I'm good. I'm set. And that's fine. Number 28, we have root 25v squared over 36, a fraction that cannot reduce, but like the other problem, we can split up the product that's in the numerator as we also split it apart with the denominator. So root 25 over root v squared, or times root v squared over root 36, all perfect squares. Square root of 25 is 5, square root of v squared is v, and square root of 36 is 6. Okay. Numbers 29 to 36 simplify the expression. Now we are dealing with cube roots. So number 29, we have the cube root of 16. Now the square root of 16 is 4. It's not square roots anymore. It's cube roots. Perfect cube numbers included. Maybe I should write this list here. 8, I'm ignoring 1, but 8, 27, 64, 125. This is 2 cubed, 3 cubed, 4 cubed, 5 cubed, 6 cubed, 7 cubed, 8 cubed, 512, I think 512, 9 cubed, 10 cubed, right? These are perfect cube values. The largest perfect cube value I can factor out of this is 8. So cube root of 8 times cube root of 2. Cube root of 8 is 2. You get 2 times the cube root of 2. The problem I have writing these often is I need to make sure the cube root doesn't look like it says 2 cubed. It says 2 times the cube root of. So I have to kind of put it over that. That's not a minus. That's part of the symbol. Okay, number 30. Cube root of negative 108. Remember, you can take cube roots of negatives. The result will be negative. Maybe we're going to get an opposite of a negative somewhere. I'm not actually sure. But the answer is negative as we pull some things out. Let's pull something out. Largest perfect cube factor, I think it's going to be 27. 27 times 4 gives me 108. So, excuse me. So let's do cube root of negative 27. Let's actually, and by the way, when I'm saying you can take the cube root of a negative, I'm saying do take the cube root of the negative. Don't leave it inside the thing. Part of it is factoring out that negative 1, if you will, or negative 27 in this case, times the cube root of 4. So we are going to take the cube root of negative 27, which is negative 3. So we get negative 3 times the cube root of 4. I think writing sideways is beneficial for this problem set. Very drill and kill-esque. Just make sure your work's organized. Notice how I'm skipping spaces. I can see some students just really cramming this in and just like going from like here to here to here to what are you doing, man? At least have some level, and box your answer. At least have some level of organization, and please show your work. Number 31, we have the cube root of negative 64 x to the 5th. All right, 64 itself is a perfect cube of 4, so straight up, when we take the cube root of negative 64, we are going to be getting negative 4. As far as this guy, the cube root of x to the 5th, I think we're now established to the point that we are dividing 5 by 3. 3 goes into 5 once, so I can pull out a single x out of there. Now, 2 x's remain. See, x squared is not a perfect cube. I would still need another power of x to be able to pull that out, and I can't. And that's what remains inside of there, right? It's cube root, maybe this is the last time I get to write this, cube root of x cubed times cube root of x squared. And cube root of x cubed is x. Cube root of x squared remains. Number 32. Negative on the outside doesn't really change anything, unless there's one on the inside. But negative cube root of 343 n squared. If you recall, 343, or if you look, 343 is the cube root of 7. So that becomes, if I break it up, negative cube root of 343 times cube root of n squared. Just like cube root of x squared can't come out, cube root of n squared will also not be able to come out. Cube root of 343 is 7. You get negative 7 times the cube root. That is not a 3. That is a monstrous 3. That is an all grown up 3. Times the cube root of n squared. Number 33. Let's go to the next page. Number 33. Oh, now we're talking. We have cube root of this fraction, 6c over negative 125. Okay, so we have a few things here. Now listen, we split things up at times. I'm going to at least split up the top and bottom. I'm not going to split up this part. I can't take the cube root of 6. I can't take the cube root of c. I'm telling you that right now. So remember what I said in the end. We put anything back together that was separate cubes inside the same term, like within a product. However, I'm going to split up these things because I can't have an irrational denominator. It's not irrational. I just can't have a radical. And I can take its cube root. Cube root of negative 125 is negative 5. So listen, I'm going to put the negative on the outside here, right? It's a part of the entire fraction. I don't want denominators negative. That shouldn't be a part of what we do. It should be assigned to the entire fraction or just the numerator. That's how we do things. That's how photomath would do things. Mr. Robinson doesn't photomath, but he agrees with what it says. Let's just say that. All right, number 34. Cube root of 8 h to the 4th over 27. Unlike the last problem, I can take the cube root of 8. I can take most of the cube root of h to the 4th, leave some behind, and I can take the cube root of 27. So I'm going to split that thing up. Remember, I imagine after this problem set, I ain't writing the split up anymore. We're just doing it separately where we can. Cube root of 8 is 2. Cube root of h to the 4th goes into 4 one time with a remainder of 1 inside of that cube root. Cube root of 27 is 3. Nothing can reduce. We're not squared away. We are cubed away. Cube rooted away. Number 35. The numbers just don't get smaller, do they? But when you take the cube root, they sure do. Negative cube root of 81 y squared over 1000 x cubed. Nothing can reduce. Negative still outside here. Let's write out their separate cube roots because we're going to be able to do it for most of them. Not for y squared. Boo hiss. Cube root of 1000 and cube root of x cubed. Okay. Cube root of 81. Not a perfect cube in and of itself. However, it does contain 27. And 27 times 3, let's not forget the negative. 27 times 3 gives us 81. Let me fix that 3. 27 times 3 is 81. We have that cube root of y squared. I can't take the cube root of y squared. It's going to stay like that. Cube root of 1000 we are going to be able to do. That is 10. And cube root of x cubed is x. So the last part's going to be my answer. Cube root of 27 is 3. So I'll have negative 3. These cannot come out of the cube root. Cube root of 3 is not 1. 1 times 1 times 1 is still 1. It's not 3. But these can come back together inside the cube root together. 3y squared inside the cube root. And I have 10x in the denominator. Now listen, we're simplifying this. I don't know if you agree that one looks better than the other, but that's not the discussion we're having. That's not what's up for debate of what looks better. It's what's simplified. The math gods and I myself would agree that I need some of this stuff going on in here. There's reasons for it, and we're going to see some of them, not just in this section, but in future sections, and especially 4.5. I believe when things can combine, things can reduce, things can work themselves out better, and we can make answers look like other ones in different methods. But furthermore, if fractions can reduce, we'd be able to. I mean, we're not arguing or debating on what looks better, and I hope that you're okay with that concept, especially when we start rationalizing denominators. Anyway, cube root of 21 over... I can't take the cube root of 21, but I do have to split it up with its denominator brethren. And it doesn't have any perfect cube factors to my knowledge, so no. Cube root of negative 64, let's make that its own, sorry. Cube root of a cubed. And cube root of b to the 6th. And again, since we're not yet rationalizing denominators, you can assume this denominator is going to clean itself up, and it sure will. Cube root of 21 stays up top, just as it was. Cube root of negative 64, oh, I'll put that in front of the negative, but it's 4. This equals, sorry. Cube root of a cubed is a. Cube root of b to the 6th. 6 divided by 2 is, or 3 is 2. And you'll have to, that is very spaced out, but 4ab squared on bottom. 4ab squared. Okay. It's 36. Okay, let's move on to some error analysis. Looking at my time. I need water. In 37 and 38, describe and correct the error in simplifying the expression. All right. Good. There's a reason I like 37, because then I don't have to do it myself later. They're showing me exactly what to do. Oh, I'm sorry. I don't want to write out what they're writing. Okay, let me point out what they're writing. Root 72 is root 4 times 18. I don't disagree as far as the math. I don't disagree that 4 times 18 is 72. I don't disagree that you can split up the square root. I don't disagree that the square root of 4 is 2. That's all perfect. These are even equivalent. If I type square root of 72, I get some value. It's somewhere between 8 and, it's probably 8.5-ish. 2 root 18, probably about 8.5-ish. They're exact. What's the problem? We simplified. We're not fully simplified. 18 still has a perfect square factor inside of it. 18 can still simplify because inside of a square root. Although it is equivalent and somewhat simplified, it is not fully simplified. 18 still contains a perfect square factor of 9, and therefore its square root can continue to be simplified. So there are two ways. Whoops. Oh, Jesus. I'm sorry. I was clicking on something. Continue to be simplified. Okay. Now there are two ways to correct the error. One way is to re-scrap the problem, which is what I want to show you to begin with. So we'll scrap the problem and redo. Let's not see, they pulled out 4. It just means it wasn't the largest perfect square factor. 9 could have been pulled out. 36 could have been pulled out. In fact, I think we did this problem earlier, but 36 can be pulled out. Root 36 times root 2, which becomes 6 root 2. Okay, so that's the faster way. And once again, I think at this point I'm going to kind of not do this as often. But let's go to the 2 root 18. So in 2 root 18, 9 can come out, right? Root 9 root 2, and 2 square root of 9 is 3. So 2 multiplies with the 3, and that's where you get the 6 root 2 again. So it's not that you can't do this, it's that it takes longer, and you might stop short, right? You might stop before you're supposed to. You have to make sure that you keep going, and this one could clearly keep going. And that was number 37. So I like that they showed the problem because I wanted to show it earlier with the kind of thing, but I always want to pull out largest perfect square factors when you can, and that's why you want to do it. Okay, let's keep going. Number 38. All right, we have cube root of, oh, I'm sorry, let's see what the heck they're telling us to do first. This is correct the error. Okay, so their 125 came out of the cube root. This should be inside of a cube root right there. Let's see if they do the top correctly, though, meanwhile. Good. Good. Okay, so their problem is the 125 was not cube rooted. The 125, I don't know how often that happens for my own kiddos. Maybe? I don't know. I don't know how often we do these problems. The 125 was initially inside of the cube root and somehow escaped the cube root in the next step. In the next step. Next step. So let's just, I'm not going to change the whole problem. They simplified the top correctly to my knowledge. It looks correct. I'm going to stick with that. I'm going to take this into 4y times the cube root of 2 all over the cube root of 125. And at that point, the cube root of 125 is 5. So 4y times the cube root of 2 all over 5. And that's your final result. Okay, looks good to me. Let's go ahead and move forward here. Give me a second. Okay. Numbers 39 to 44. Now, looks like we're supposed to rationalize the denominator, but we're actually not rationalizing yet. It's baby steps. They're telling us what number, what factor, what would we multiply top and bottom by to rationalize the denominator. And they're just asking for the single number. They're not saying actually write it on top and bottom, which is interesting. So I'm just going to copy down the problem, then I'm going to give you the answer. This monomial root 6, if I multiplied everything by root 6, all would be good. I think that's all I write. We're going to rationalize later after this, but that's all we write to begin with, okay? Number 40, 1 over root 13z. 13z, or root 13z being irrational, we would have to multiply top and bottom by root 13z. Okay? These are kind of interesting baby step problems. It's good for me because doing 100 problems makes me feel a little nicer about this. Okay, this is one where I'm going to go more in the form of how they didn't talk about it, but they did an example this way. Just multiply by enough so that you so that you rid yourself of the find a perfect cube after you multiply by something. So what would I have to multiply this by? What would I have to multiply x squared by to get a perfect cube? I'd have to multiply by x. X squared times x is x cubed. So let's multiply everything by the cube root of x. This would net me a perfect cube. And I think that's the perfect way of putting it. I don't know why I didn't really talk about that in the past, but that totally works here. And I think that leads into this next problem, number 42. And I think it's good we have these baby steps to start off with rather than everything else we have to throw into it. So 3m over 3m over the cube root of 4. So the same thing here. I can't even copy the problem. It's so hard. It's not going to be cube root of 4 or cube root of 4. I need to multiply by something that's going to net me a perfect cube inside there. And the smallest one possible. In this case, 8. I can multiply top and bottom by the cube root of 2. Cube root of 4 times cube root of 2 is cube root of 8, which gets us 2. And that's what's going to work there. So cube root of 2 is totally fine. Number 43. This is where we have a binomial in the denominator and just multiplying by, say, the square root of 5 or something is not going to pan out. This is where we start to multiply by conjugates. The square root of 5 minus 8's conjugate is the square root of 5 plus 8. This is what you're going to multiply by in top and bottom. Create a difference of 2 squares. I'm going to go through those relatively fast when you do them on these problems because I already did them and saw them in the lecture portion. But it creates a difference of 2 squares in a plus b minus a plus b times a minus b scenario, which turns into a squared minus b squared. And that's what this is going to have as well. Another conjugate, we got to multiply by root 3 minus root 7. It is the only, I'm not sure if I'm being facetious or sarcastic or exaggerating. It is the only thing you can multiply by to eliminate the radicals in one step. There's nothing else you can multiply by other than this to clear it up. Literally, it's not that, oh, this is fun, this is easier. It's the only thing. That's the only thing. Okay, we're going to start simplifying these expressions. So now we're actually going to start rationalizing these denominators. So now we do find that thing that we multiply by. So for 2 over root 2, we are going to multiply top and bottom by the square root of 2. Now the reason we do this is because the square root of 2 times square root of 2 is 2, and on top we get this 2 root 2. Now, we would be done if nothing could reduce, but 2 divided by 2 can become 1, so we are going to be left with just the square root of 2. Yes, these are equivalent. 2 root 2 is equivalent to square root of 2. It's, if I remember my, oh wait, never mind. It's around 1.4 something. It's around 1.4 something. Okay. In fact, this makes sense. The square root of 2, ask yourself what number do you multiply to itself to get to, so that's the square root of 2. And if I divide 2 by the square root of 2, I should get another square root of 2 out. I mean, that I should be able to answer that without rationalizing something. I think that made total sense, actually. Maybe it only made sense in my head. Number 46, we have 4 over the square root of 3. We are going to multiply top and bottom by the square root of 3. Remember, it must be both because we are effectively multiplying by 1. We're not changing the value of our answer, we're just changing its appearance. We did this because root 3 times root 3 is 3. We're left with 4 root 3 on top. Now, nothing can simplify further. Remember, I am not canceling these 3's out. This is inside a radical. This is not. Remember, this is not 3. This is like 1.7 something, right? It's not 3. So don't try and reduce it with things that are not in irrationals with it together. Number 47, we have root 5 over root 48. Okay, there's more than one way we can do this problem. Let's talk about the way that I would not prefer, which is multiplying by root 48 over root 48. Oops. Over root 48. Okay. Root 48 times root 48 is 48. All right, that's fine. Root 5 times root 48. Now, there's more than one way to do this part as well, but as long as I'm dealing with this big number here, I'm going to deal with this big number as well and just play with it. Root 5 times root 48 is root 240. And now we have to find a perfect square factor in 240, the largest one possible that's going to work out here. So clearly 4 works. 8's not a perfect square. I think 16 works. I know 16 works. In fact, it's 16 times 15. So I think that's the biggest one. So root 16 times root 15. I promised I wouldn't do that, but I just did. Which is 4 root 15. And 4 root 15 over 48, 4 over 48 can reduce to 1/12. So you get root 15 over 12. And that's the answer. However, when I said there were 2 ways to do this, here's the other way to do it. Or root 48 itself can simplify already. 48 has a perfect square factor of 16. Here's where I'm going to do this mentally with you guys. Root 16 times root 3 becomes 4 root 3. Now, why does this help? And by the way, what do I also multiply by? It helps because now I get to multiply by what's apparently a smaller number, or something that's already more simplified. Now, the other part that makes this easier is, do I multiply by 4 root 3 over 4 root 3? No, I don't need to, because 4 has nothing to do with rationalizing this. Root 3 is the part I need to rationalize. I'm just going to multiply top and bottom by root 3. That's the only part I need to multiply by. Root 5 times root 3 is root 15. Root 3 times root 3 is 3, and 4 times 3 is 12. So I'm done there. Much faster, much smaller, much simpler. That's what I like to do first. I like to simplify first, make my numbers smaller. So this OR, you're going to see me only do the OR exclusively as long as I can handle what's going on underneath, if that makes sense. All right. Number 48. We have root 4 over 52. Now, the immediate thing you need to do here is split this up into 2 radicals. I'm done writing as 2 separate radicals. I'm just going to take their square roots if I can. The square root of 4 is 2. Square root of 52, on the other hand, excuse me, it's 13 times 4. So, 4 times 13. You can simplify a 4 out of there. So this becomes root 4 times root 13 or 2 root 13. Great. 2 over 2 is 1, so you're left with 1 over root 13. Now, I'm not done because I haven't yet simplified my radical, but I'm now dealing with a smaller value. And that's it. And now listen, I did this even slower than I probably should have here. Root 4 over 52 could have reduced in and of itself. This could have been root 1 over 13 immediately, and I would have gotten to here. So, either or. I don't even know if I noticed that. That's kind of sad that I didn't. Now I can multiply. I got to rationalize this. I got to multiply top and bottom by root 13. Which then becomes root 13 over 13. Cannot reduce. You're done. That's it. But they're equivalent values. This is equivalent to this. This is just the simplified version. Whether or not you like it, it is. 49, which is a perfect square. 3 over the square root of a. Looks like they're all variables the rest of the way, or they involve them at least. We're going to multiply top and bottom by square root of a. This shall rationalize. And we're left with 3 root a over a, as much as you can do there. We're all done. Nothing more. Number 50. maybe halfway home-ish. 1, I think after doing these problems, I'll feel a little more halfway home as an overall time, because the lecture and everything involves, even though we're going to hit word problems, we are more than half the problems done. 1 over root 2x, we can multiply top and bottom by root 2x. Why not? Well, I think it's what you're supposed to do. This gives us 2x on the bottom and root 2x on top. Nothing can reduce because 1's inside a radical and 1 is not. Number 51. That is a 51. Root 3d squared over 5. Okay. Splitting up the radical, I can take the square root of d squared to get d. I cannot take the square root of 3, so I'm good there. Square root of 5 is where the rationalization is going to happen. So we're going to multiply top and bottom by root 5. Root 5 times root 5 is 5, and root 3 times root 5 is root 15. There's still a d on the outside. That did not change. Root 15 cannot simplify further, so we are finished. Number 52. We have the square root of 8. This is already split. But we have the square root of 8 over root 3n cubed. Okay. Square root of 8 is root 4 times root 2. So that gets us 2 root 2. Again, I said I'll go faster on those. N cubed, you can't take the square root of 3, but n cubed, you can divide 3 by 2, you know. It's you get n root n. N times the square root of n. That 3 is still inside that square root. So root n cubed is n root n, and root 3 remains inside with that. So let's rationalize this root 3n guy here. That's the part that matters. And like I said, I like simplifying the stuff on the bottom first to just make things smaller. I mean, I think it's going to... I won't have to simplify more on top again and reduce afterward, at least not as much, if that. This becomes 2 root 6n. That 2 times that 3 multiply. On bottom, root 3n times root 3n is 3n. So now I have n times 3n, okay? Or 3n squared. Let's just write that now. 3n squared. It doesn't look like I can reduce anything else either. 2/3 is good. No other n's outside of there. That's going to be it. And 6n, by the way, cannot reduce anymore inside the, or cannot simplify more inside the radical. Number 53 and 54, we have some cube roots. We have 4 over the cube root of 25. Now, in the past, I would have multiplied by something more substantial. I guess the smallest perfect cube is 125. So I'm going to multiply top and bottom by just cube root of 5, because that's what's going to get me that 125, right? This is, I'll just write that one to begin with and just kind of make my point in what I was going for. Perfect cube. On top, I have 4 times cube root of 5, and cube root of 125 is indeed 5. So I get 4 times the cube root of 5 all over 5. So good. I like how quickly I can explain. I don't know if that means you get it, but I've had so much coverage that the initial problems should be explaining away what it is I'm doing so quickly here. That's kind of my hope. Cube root of 1 over 108y squared. Cube root of 1 is 1. I'll leave it be. Cube root of 108, 27 is a perfect cube inside of there with times 4. Cube root of 27 is 3. So I get 3 times the cube root of 4. Y squared is not a perfect cube. It's going to stay inside of there. I want to make sure I said that correctly. 27 times 4 is 108. Yes. 4 is not a perfect cube. Yes. Okay. So moving forward, we are now going to multiply. Oh, this is interesting. I have the variable and the number to look forward to multiplying here. I got to multiply cube root on top and bottom of whatever that thing is right there. That's really going to help. See, I'm glad I don't have to multiply by cube root of 108y squared over cube root of 108y squared. Just cube root of enough here. You know what? Getting a 2, 4 times 2 would give me 8. 8's a perfect cube. And just a y. Yeah, that's going to be enough right there. That looks good. I really like that I'm following the book in that manner. I don't know if I really would have done that before, so I'm glad I am. Excuse me. I got 1 times this is just this guy. Cube root of 2y. So on bottom, check this out. I got 3 times... Why did I multiply by these? Because 4 times 2 is 8, and cube root of 8 is 2. Y squared times y is y cubed, and cube root of y cubed is y. 3 times 2 is 6. You're going to be left with the cube root of 2y over 6y. Why not? And that is, excuse me, that is simplified. Water break with my hiccups. Actually running out of water. I think I should refill soon. Okay, 55 to 60 simplify the expression. Now we are going to deal with binomials in the denominator, which means we have to now multiply by conjugates. Maybe on the first problem I can slow down the difference of two squares portion a little more to show you exactly what's going on. 1 over root 7 plus 1, we've got to take care of this. The only way, guys, is multiplying by this guy's conjugate. The conjugate is keeping the sign of this guy and changing the sign of this guy. Root 7 minus 1 over root 7 minus 1. A plus B's conjugate is A minus B. Like that. Now, why do we do this and what do we do with this? First of all, you got to treat everything inside here like quantities, parentheses, if you will. I'm not going to write this in the future, but you treat it like that. As in 1 would distribute into these two, which is no change, right? That's just root 7 minus 1. But on bottom, you are, effectively, you're foiling. Root 7 times root 7 is the square root of 7 squared, right? I mean, it's 7, but I want to kind of make the bigger point in what I'm doing here. Root 7 times negative 1 is negative root 7. 1 times root 7, I mean, listen, it's the difference of two squares, is 1 plus root 7, and 1 times negative 1 is negative 1. What happens is, minus 1 squared. What happens is you cancel out these two ones that have radicals, and when you square this radical, you're not left with a radical anymore. So now I got root 7 minus 1 over root 7 squared minus 1 squared. This is your a plus b times a minus b is a squared minus b squared. That's what we're doing here. Squaring a, squaring b. That's the slowest I'll go on those problems in the future. Not going to go that slow. Root 7 squared is 7. Root 1 squared is 1. And 7 minus 1 is 6. So I get root 7 minus 1 all over 6. And that's it. Some of these we're going to have to do a little bit more when it comes to the reduction process and stuff like that, and we'll be all good. Now, 56 is the last problem where I'm going to show the actual squaring of these numbers, and hopefully I can say it out loud and it'll be good. But I got 2 over 5 minus the square root of 3. Its conjugate will be 5 plus the square root of 3. This is what will provide me those difference of two squares. Now, I'm not going to write the parentheses, but keep in mind what will happen. It's a distribution. We're going to have 5 squared minus root 3 squared. And on top, 2 will distribute into 5 and root 3. It's not just 2 times 5. So it's 10 plus 2 root 3, okay? Now from here, I still have 10 plus 2 root 3. Excuse me. And on bottom, I have 25 minus, not 9, but square root of 9, which is 3. 25 minus 3. 25 minus 3 is 22. So 2 root 3 here over 25 minus 3 is 22. This is where this might be new for you, but these fractions can reduce because they need to all, listen, there's a common factor of 2 on top. This is kind of how you need to say it. 2 is a common factor on top, and then the common factor divides and reduces with the one down below. These can all divide by 2. These can all divide by 2, and that's what we're going to do. 10 is divided by 22, 2 root 3 is divided by 22. We are left with 5 plus 1 times the square root of 3 all over 11. This is the final answer. Not this, but this here. Number 57. As I start to work faster on the stuff on the bottom, we're going to get root 10 over 7 minus root 2. We are going to multiply top and bottom by the conjugate. So on the top we distribute. We got 7 root 10 plus, now root 10 times root 2 is root 20. Now on bottom, we get to do 7 squared, 49, minus root 2 squared, 2. Okay, on bottom we have 47. Let's leave that, see if there's anything we can do at the top here. We have 7 root 10. Now the square root of 20, listen, root 10 doesn't have a perfect square factor. Root 20 has a perfect square factor of 4. Root 20 is root 4 times root 5, or 2 root 5. And you get 2 root 5 all over 47. 47 is a prime number. These are not numbers that are factors of 47. Excuse me, multiples of 47. So, we're good. That's it. These can't combine, by the way. We're going to talk about combining things later. Number 58. Root 5 over 6 plus root 5. Okay, we'll multiply top and bottom by its conjugate of 6 minus root 5. And on top, we get root 5 times 6 is 6 root 5. Root 5 times negative root 5 is negative 5. Right? I mean, it's the same way as we're going to square these negative 5s as well. Now we get 36. Listen, I'm just going to write it. 36 minus 5. It's 31. We're doing 36 minus 5. 31. I think that's it. I can't do anything else with that. So hopefully, again, hopefully you're starting to see the speed, I'm not trying to make it fast, but just you're feeling out the efficiency of what we're actually doing. Maybe you don't know why it is. Maybe you don't agree with the concept. You're like, this looks weirder than this. I don't care. Math gods don't care. It's simplified. It's what simplification does. Whole numbers in the denominator. So it's not up for discussion. 3 over root 5 minus root 2. We're going to multiply top and bottom by the conjugate. And listen, I'll deal with the bottom first. The whole point is that we rationalize the bottom. Otherwise, there's no point in doing what we're doing here. Root 5 is 5. Root 2 is 2. 5 minus 2 is 3. Now, 3 is going to distribute into both of these. However, we might as well keep it factored out because we have to divide all these by 3. 3 and 3 can divide by 3, and we'll be left with these all being 1. 1, 1, 1. And 1 root 5 is root 5. 1 root 2 is root 2, and divided by 1 is just that. You get root 5 plus root 2. Here's where simplification, I think we can all agree, looks better. It looks better. And by the way, that's not root 7. Don't start doing that. But root 5 plus root 2 looks a lot better than 3 over root 5 minus root 2, at least to me. No one here likes fractions, so, we dealt with it. Sometimes it even makes it look better. All right, number 60. Root 3 over root 7 plus root 3. Now, I'm not sure how much I've had to talk about this, but don't be silly and start doing this, please. It's not a common factor. It needs to be a common factor on top and bottom. That is not one. Separate terms. Okay. Anywho, we're not equal to anything. Let's multiply by the conjugate of root 7 minus root 3. Looks like word problems come next. All right, what's the whole deal with the bottom? Got 7 minus 3. Again, root 7 squared minus root 3 squared. 7 minus 3 is 4. Now I got root 3 distributing into root 7, which is root 21. Root 3 times negative root 3 is negative root 9, which is negative 3. Root 21 minus 3 over 4. That's all it becomes. Root 21 doesn't have any perfect square factors. Yeah, we're good. It's working out. Okay. Number 61 is the start of some word problem bits. I guess later they do I guess the example order is the same as the order of these kinds of problems. And for the examples, they don't do the operations until the end, which I'm glad that we get to finish off with something pretty fast here. How far are we along? Okay, hopefully way past halfway done. I think I mentioned that earlier. Modeling with mathematics. The time t in seconds it takes an object to hit the ground is given by t equals square root of h over 16. Now, automatically, I'm seeing this and saying, hey, guys, can we just rewrite this as square root of h over square root of 16 or square root of h over 4? I hope I can use this and, work that out. Anyway, h is the height in feet from which the object was dropped. So what they say? So the time something hits the ground based on your height, you can do this. I think I agree with that and understand why that works. It's a gravity thing. What are we going to do with this? How long does it take an earring to hit the ground when it falls from the roof of the building? The building is 55 feet tall. So with h being 55 feet, we're going to substitute that in for t, and for h, and we get t is the square root of 55 over 4 seconds. But of course, this is probably one of those things because it's like a word problem. Let's round it. I'm going to pop up my calculator. You don't have to see it, but square root of 55. Just make sure you close the square root on 55, or leave it as it was and divide it by 16 inside the square root. Yeah, it's up to you. Divided by 4, it's about 1.85 seconds. 1.85 seconds. Yeah, that earring might get a little bit of air drag, but that's not coming to effect. How much sooner does the earring hit the ground when it's dropped from 2 stories below the roof? 2 stories below the roof. Wait. So at 33, so h is 55 minus 22, which is 33 feet. Okay. So on this problem, I couldn't tell if they meant 22 feet above ground or below the roof. So now we're going to say t is square root of 33 over 4, substituting that for h, seconds. So square root of 33 all divided by 4, and that's going to be 1.44 seconds. Now, I'm rounding early, and I feel bad on this because, listen, this isn't the answer. They said how much sooner does it hit the ground. Listen, I could have done one of two things here. I could have done what I just did, but I'm not done because now I have to take the difference. Wait a second. Yeah. I'm trying to think if there's more than one way to do this. I'm trying to think if I could substitute 22 and just be done with the answer. I feel like I can't. I'm not going to try. But anyway, this is dropped from 33 feet instead of 55 feet. So now we got to do the distance between those, the difference, the 1.85 minus 1.44. So I'm going to use the exact values that were in my calculator, okay, and subtracting those and then round to the nearest hundredth for that. So it's around 0.42, which actually would not work. 0.42 seconds, which you're probably saying, Mr. Robinson, 1.85 minus 1.44 is 0.41. Yeah, but let me show you what I'm doing in my calculator here. Whoops. I did root 55 over 4 and root 33 over 4, and I'm using the exact values. I'm taking root 55 over 4 minus the previous answer, and it's 0.417. That rounds up to 0.42. So that's why rounding early is never a thing that you want to do. Remember, this was 0.44 rounded right there, but it's not quite exact with that in mind. So anyway, 0.42 seconds is my go-to. Is that the question? How much sooner does the earring hit the ground? 0.42 seconds earlier? Because of the nature of what we're doing on the problem. Okay. That was all of number 61. Number 62. Yeah, this will be a slowdown. The orbital period of a planet is the time it takes the planet to travel around the sun. You can find the orbital period P in Earth years using the formula P equals square root of d cubed, where d is the average distance in astronomical units of the planet from the sun. So I'm trying to think about it with Earth. Well, I guess I'd have to know the average distance, and I don't know it. Simplify the formula. Okay, so I was actually going to do that. I'm surprised they didn't ask us to do it in the previous problem. So, okay, part A, simplifying it is taking the square root of d cubed. So that'll be d times the square root of d. It might not look better to you, but it is simplified. Part B, what is Jupiter's orbital period? So Jupiter's is 5.2 astronomical units. I guess I'll use the simplified version. So 5.2 root 5.2. And this is in, I didn't see what this is in. Earth years? Is that the unit? The orbital period is in Earth years. Earth years. Now that's exact. Let's round it because I'm much more curious as to seeing an exact number where I can. 5.2 times the square root of 5.2. It's going to be somewhere a little more than probably 12, 11 or 10 or so. Yeah, 11.85. Sorry, I'm seeing it on my calculator. 11.857. I'm going to do 11.86 Earth years. It takes about 12 years for Jupiter to orbit the sun. I was wondering how long it would take Earth to orbit the sun in Earth years. It'll take 1. I think the real question was how many astronomical units away is Earth from there, and we could totally just plug in 1 for P and kind of figure it out, but I'm not going to. Okay, number 63. I had to buy one of these for something. What was it for? I bought it recently. It was for a it was for my amp. Whoops! It was for my amp for my receiver for my subwoofer to see if it was drawing any power. I had some problems with it. No, it was checking for the battery. Okay. The electric current an appliance uses is given by I equals root P over R, where P is the power in watts and R is resistance in ohms. What's funny is I always swap amperes watts and ohms. I would remember if I took when I took junior year physics in high school. I don't remember anymore. Find the current an appliance uses when the power is 147 watts and the resistance is 5 ohms. It's just a substitution, guys. Don't be too phased by the word problem. I'm just saying I can't remember what is what on here. Like, I had trouble with this device. I said, what do I do? Because look, there's so many dials on this thing, guys. It's crazy. Anyway, I think I figured it out through YouTube. And now I'm paying it forward by substituting 147 for P and 5 for R. And listen, they were simplifying ones before, so I'm going to continue to do that. Whoopsie. So 147, it's not a prime number, but I don't think it has a perfect square factor. Oh, it does. It's 49 times 3, so time out. This is root 49 times root 3, which is 7 root 3. I never would have even guessed. Anyway, I figured it out, but I can rationalize this with root 5 over root 5. I know I'm getting exact here, right? But we will do the rounded after. So this becomes 7 root 15 all over 5 amperes. That's an exact. And approximated, which I could just use the original. Here, let me show you this. Because so far you're just believing me and seeing that everything is the same. Root 147 all over, what was the number 5? Is this value here, which is our answer. Excuse me, but let's look at, what was my other number? 7 root 15 all over 5. 7 root 15, and close the parentheses this time, all over 5, and same value. I'm all out. So when we simplify, I'm gonna get some more. When we simplify, we're not changing the value, just changing the way that it looks. So I'm gonna write 5.42 amperes about. Okay, so that's what we got there. Either or as an answer, exact and simplified, and then rounded. Which is what the reading would probably say on the screen, though. I'm sure it's not going to say 7 root 15 over 5 on the screen. All right, more modeling with mathematics. You can find the average annual interest rate in decimal form of a savings account using this formula, of which I wasn't aware. I'm sure it's just a rewrite of the other formulas I do know. V naught is the initial investment, and V sub 2 is the balance of the account after 2 years. Use the okay, then I do understand this formula, actually. I just don't write it this way. Use the formula to compare the savings accounts. In which account would you invest money? Explain. All right, so we have 5 accounts. We have initial investment and balance after 2 years. I guess we're going to kind of plug and chug. We're going to take a look at all of these and compare which one has the largest interest rate is our goal. We want to invest money in the one with the largest interest rate. So we want to see which ones grew most over time. We don't just look at which one, hey, this one has $406. I should use this one. No, because you started with more money on this than the other one. So you have to see kind of how they're comparing their growth over the 2 years of time to make sense of it down the road. So I don't know if I want to write some stuff within, I guess. So account 1, we're going to be doing R equals, and listen, I'm not going to simplify all of these. Okay, I'm just going to compute them. So 293, that's the final after 2 years, over 275 minus 1. We'll see what that becomes. Now these are decimal values that have a percentage equivalence that I will write at the very end of this one. Account number 2 is going to be R equals 382 over 361. You're like, gee, after 2 years, you only got $20. I mean, listen, I think they're making more than I get in my accounts. That's why it's all about the stock market now. Account 3, we're going to get square root of 214 over 199 minus 1. Ugh, my ears are plugged. Account 4, we have R as square root of 272 over 254 minus 1. And then account 5, we're going to do r equals square root of 406 over 386 minus 1. We'll figure out what those values are. They're probably not perfect, but we're going to be able to compare. Now listen, I'm going to be on the graphing calculator. Sorry, you can't really see everything. I'm going to be on the graphing calculator window with you guys, and I'm going to write these ones down while I'm still in the window so you can just see what I'm typing in and how I'm replacing things kind of in the faster realm. So I'm going to start with the square root of 293 over 275. I got to close those parentheses and put minus 1. So the first value is around 0.0322. 0.0322. I'll do 4 decimal places for each of these. I don't know how close they'll be. I'll recall the previous answer and now put 382 over 361. And it's still minus 1 there. That's smaller. So 0.028, rounding that up to 7. The next one, we'll do 214 over 199. See, these are parts of the video where I could pause. I mean, I'm going, you know, I still have to take time to do this, but this is stuff where I don't know how much it matters to you. Next part is, I think you have to suffer the pain with me. No, you can totally fast forward this, unless you run into an advertisement. This is brought to you by whatever you buy. 0.03, I haven't compared which ones are actually bigger yet. I just know that one had a 2 in it. 0.0348, and the last one is 406 over 386. Watch it be the biggest, even though I was crapping on it earlier. I don't think it will be. I think it's the smallest. After this, I'm going to get more water. Excuse me. Okay, so let's compare these 5 values right here. Now, these are interest rates. These are the decimal equivalent of some percentage. This is like 3.22%, 2.87%, 3.7%, 3.4%, 2.56%. Account 3 yields the largest interest rate. I'm going to type this. Okay, that's what I wanted to put there. Okay, I'm just hiccuping over and over. I can barely talk. I'm going to get water. Okay, we'll see how I last here. I got my big jug. I'll have to pause in between, though, because it's probably loud and rattly. All right, so account number 3 yield the largest percentage in interest rate and such. So you want to select that one. So what was the question? In which account would you invest money? So I would invest money in this one. I would invest money in account number 3. I don't know how. I just want to say what what I need to say, and that'll be it. Okay, let's move forward. Number 65 to 68. Evaluate the function for the given value of x. Write your answer in simplest form and in decimal form, rounded to the nearest hundredth. Okay, so we're simplifying. Okay, so h of x equals root 5x, where x equals 10. We're going to take h of 10. I don't know. Okay. So root 5 times 10. I'm just saying I don't know what they're bringing about with us doing this. There's practicing function notation, I suppose. Square root of 50. Now, square root of 50 is root 25 times root 2, which is 5 root 2. That is the exact answer. The approximate answer rounded to the nearest hundredth, that's 2 decimal places. I'm not going to show my screen. I know it's 7 point something here. 7.07. 7.07. That's the nearest hundredth rounded. And I'm just going across the screen like that to save myself some paper. Number 66, we're looking at g of x equals root 3x. G of x equals root 3x. And let's look at x equals 60. So we're going to take g of 60. And we're going to get root 3 times 60, which is square root of 180. 36? 36 times 5, I think so. So root 36 times root 5 is 6 root 5. And, by the way, I'm typing square root of 180 in my answer here whenever I do this. Square root of 180 is 13.42. 13.42 approximated. So exact and approximated. Again, 36 times 5 is 180. So like I said, that's where I'm doing the I'm going faster thing. Not writing the in between. No more. If you can come up with it, go for it. Oh, I might have to write it here. Let's see what we're doing. R of x equals root 3x over, oh, we are practicing some of the function notation stuff, 3x squared plus 6. We're practicing order of operations here, folks. X equals 4. Okay, let's take R of 4, shall we? R of 4 is 3 times 4 over 3 times 4 squared plus 6, which is the square root of 12 over 4 squared is 16 times 3 is 48 plus 6 is 54. Okay. Instead of splitting this up first, I'm going to reduce the fraction first, okay? So let's begin by dividing to 6. Divided by 6, I get 2/9. Yeah, this is perfect, because I don't have to rationalize anything, because on top I get the square root of 2, and on bottom the square root of 9 is 3. I just wrote 9. The square root of 9 is 3. So I get root 2 over 3, and I'm good. Now I still do have to compute what this whole thing is, and I am going to this time do root 2 over 3. That's quicker. So root 2 over 3, and I'm trusting my answer. I believe I can get something wrong. Bank on it, and correct me in the comments if I ever do mess this up. I'm getting 0.47 when rounded to the nearest hundredth on that. All right, number 68. P of x, at least these problems are relatively fast. P of x is the square root of x minus 1 over 5x. And we are evaluating for x equals 8. We're simplifying. Assuming these can all simplify. So we get the square root of, we can probably do this in our head, right? 8 minus 1 is 7. 5 times 8 is 40. Okay. Before I rationalize, I will split these up, and in splitting these up, square root of 7 on top, square root of 40 on bottom, root 4 times root 10 gives me 2 root 10. Now I go to rationalizing. I'm only going to multiply top and bottom by that root 10. Let's go down to the next step. Well, I can fit it here. Root 7 times root 10 is root 70. And on bottom, I get 2 times, root 10 times root 10 is 10. So 2 times 10, which is 20. Now, I have to make sure root 70 doesn't have any perfect squares, and it does not. So I'm good there for the exact. The approximate, I'll type root 70 over 20 on here. Root 70, close parentheses, over 20. I'm getting 0.42, 0.42. Okay, there's 68. Feeling it in my neck now. 2/3 through, 69 to 72. Evaluate the expression when A is -2, B is 8, and C is 1/2. So the same kind of stuff. We're just substituting these specific values for these here. So A is negative. Let me write this below. A is -2, B is 8, C is 1/2. All right, here we go. So number 69. Square root of A squared plus B times C. All right, we're going to get square root of -2 squared plus 8 times 1/2. This is square root of 4 plus 4, which is square root of 8. See, this is why I don't like to do the left to right stuff. Generally I wouldn't do this kind of thing. I just felt like it here. Square root of 8 is 2 root 2. Root 4 times root 2 is 2 root 2. The approximate to the nearest hundredth, 2 decimal places. Square root of 8, I used to know this. 2.83. 2.83. Okay. 70. Negative square root of 4c minus 6ab. Here's what I'll do. I'm going to put it underneath. Not for all of them, just my first step when I substitute. Negative square root of 4 times 1/2, that's c, minus 6 times negative 2 times 8. So negative square root of 4 times 1/2 is 2. All right, I have negative 6 times negative 2, which is 12, positive 12, times 8 is 96. So plus 96. So negative square root of 98. Okay. 98 is 49 times 2. So root 49 is 7. So negative 7 root 2. Now this number is going to be very close to negative 10 because the square root of 100 is 10. So this is about probably negative 9.92. I have no idea. Let's see. Square root of, I'm going to say 98. 9.899. So 9.90. Negative 9.90. That's rounded to the nearest hundredth. A lot of people have trouble rounding that kind of thing, right? It was 9.899. People have trouble going like, how do I round to the 2 decimal places? This is a 0. You just round and kick it up. Don't ignore it. Number 71. Oh, I didn't change the thing before. Sorry. That tends to happen. All right, number 71. Like I make it better by me doing that. Like, look, guys, I moved it over. It's like someone using the blinker after they turned into the lane. Not that I've had experience with that recently. All right, negative 2a squared. What was it? Negative 2, 8 and 1/2. Negative 2a squared plus b squared. So there's no c. So I got negative, opposite of negative, square root of negative 2 times, or 2 times negative 2. I shouldn't speak. Plus 8 squared. I should just write. I should just write and then say what I wrote, not write what I say. Negative 2 squared is 4, times 2 is 8, plus 8 squared is 64. So negative square root of 72. I think they're trying to see if you can keep the negative the whole time, because people tend to lose it. 72, I think we've done this a lot. 36 times 2, so 6 root 2. Negative 6 root 2 is exact. Approximated. We might have even approximated it earlier. Did we? 8.449. I don't really remember that number. Negative 8.49. 8.485. Negative 8.49. And then number 72. B squared minus... Oh. You're going to learn about this b squared minus 4ac someday. You're going to learn it on section 4.5. The square root of b squared minus 4ac. You betcha. Now, for the specific numbers, negative 8 or negative 2 and all that kind of stuff, I don't know. But actually, you know what I was going to bring up was over here. I was going to bring up, this reminds me of making sure you know how to multiply negatives together for this very reason right here. So, when you start using quadratic formula. I'm speaking before. I don't know why I'm smiling about, oh my gosh, guys, I know what this is and you don't. It's not that. It's whenever I think about saying something and then it comes up in that conversation in the book when I'm like, they're thinking what I'm thinking. 8 squared minus 4 times negative 2 times 1/2. Now, it's not very common when I do section 4.5 with you that my a is going to be negative. However, do not forget to do minus negative and turn it into plus. I think that's the big thing I want to say. 2 times 1/2 is 1 times 4 is 4. So we get root 68. Okay, 68. 34 times 2. I don't think that can simplify. So I think I'll leave it there unless I messed up somewhere. B squared minus 4. No. So we're good. That can't simplify. Still got to round it. A little more than 8. 8 point something. Root 68. Square root 68. Oh, wait. 34 times 2. Yeah, I can. What am I I can divide it by 4. I'm sorry. Yeah, you can simplify that. I apologize. I was thinking that 17... I don't know what I was thinking. You can simplify this. This is 4 times 17. So 2 root 17. I apologize. I was sitting there thinking, like, you know what? Maybe the problem, they wouldn't ask me to simplify and then not simplify. So 8.25. 8.25. I'm surprised I didn't see that 68 for what it was. Okay. That was number 72. 73. I hope I don't have to read that. The text in the book shown forms a golden rectangle. What is the width W of the text? So your golden rectangle ratio, your golden ratio is, I shouldn't use semicolons, 1 plus root 5 over 2. So when we use 1 plus root 5 over 2, that is the length to the width. 1 plus root 5 is larger than 2. So the width is the unknown. That's our W. That should be equivalent to there. And this is 6. So that's our setup. We're just, the golden ratio just have the same ratio of 1 plus root 5 here to 2 there, right? 1 plus root 5 to 2. So they're similar with each other. We just got to figure out W from that. So we're going to cross multiply. Cross multiply here. Now, 2 times 6 is 12. And W can distribute. I don't know if I need to. I don't want to distribute. W multiplies by 1 plus root 5. We're going to divide both sides by 1 plus root 5. So W is 12 over 1 plus root 5. Now, they said, what is the width of the text? Now, I'll do the rounding on top of this, but of course, we do need to simplify what's here. We need an exact answer simplified. So we're going to multiply top and bottom by 1 minus root 5, the old conjugate. There. And that gets us 12 times 1 is 12 minus 12 root 5 here. And here, 1 squared minus root 5 squared, that's 1 minus 5, which is negative 4. Now, these can actually divide. Forget reducing a fraction. These can actually divide. 12 divided by negative 4 is negative 3. Negative 12 divided by negative 4 is positive 3. Negative 3 plus 3 root 5 inches. Is this inches? Yeah. Width of the text. That is the width of the text right there. Exactly. It's approximated to, let's see that, negative 3 plus 3 root 5. It's approximated to 3.71 inches. 3.71. Which is the golden ratio. All right, number 74. The flag of Togo. I just didn't want to say like the sandwich place, but I think it is approximately the shape of a golden rectangle. What is the width of the flag? Okay, so no real difference from the previous problem. So, I'm not really copying down the flag. I hope that's okay. I probably should be. Let's see. I didn't do it for the previous problem. Apologies, but we're past it. It's done. All right. So, again, I'm going to use just my golden ratio that you saw before. Not mine. The 1 plus root 5 over 2. And I want to explain what it is. I just don't. Okay, golden rectangle is a very quick explanation. Here's what it is. And I'm not going to draw it perfectly at all. It is built in such a way so that if I drew another golden rectangle inside this one, I create, if I draw a square inside of here, I create another golden ratio right here, another golden rectangle right there. And then when I draw a square inside here, it makes another golden rectangle. And when I draw a square inside in here, it makes another golden rectangle. And I draw a square inside in here, it makes another golden rectangle. Draw a square. And again, I probably didn't draw it perfectly, but that's what it does. That's what it does, basically. Okay, anyway, when you cross multiply here, same ish is going to happen, though this time 2 times 42 is 84, and I have W times 1 plus root 5. I'm going to multiply. Hey, listen, it's the same thing we're doing. We're going to multiply by the conjugate and all that. So 84 over 1 plus, it's the same thing we're multiplying the conjugate by, but it's a different number on top. So, I mean, we could have probably made this a lot faster as far as what the answer looks like. It'll look familiar to the last one. So this is going to be 84 minus 84 root 5 all over negative 4. So as long as we're finding widths, the smaller part, then these will kind of look the same. So now we divide these by negative 4 again. Only this time is 84. 84 divided by negative 4 is negative 21. And this is plus 21 root 5 inches. And look, it's just 7 times bigger than the previous answer. I think I can just multiply this by 7 and I'll be good. Times 7. 25.96. 25.96 inches. Flag. There we go. Okay. Actually, I could have done it from the beginning. This was 42. This is 6. This is going to be 7 times bigger. Yeah, totally should have done that. But I got to treat each problem separately. I don't know what your teacher's giving you. All right, so if you were just given 74 and you kept hearing me say it's the same as 73, well, look at 73 for a second. All right, number 75. Okay, 75 to 82, simplify the expression. This is where we get to use operators to combine like terms, like radicals, whenever they exist. And if they don't exist, we don't combine them. But if they can simplify, we simplify and see if we can combine. So root 2's can combine here. It's like x's, like negative 2x plus 6x. And this is like a y here that does not combine. Negative 2 root 2 plus 6 root 2 is positive 4 root 2. And I'm just going to write it just like that. Number 76. The root 5's can combine. And that first root 5, make no mistake, that is a 1 root 5. So 1 root 5 and then minus 8 root 5. That'll give us a negative 7 root 5, right? 1 root 5 minus 8 root 5 is negative 7 root 5. And then I have a minus 5 root 13, which does not combine and does not simplify, and this will be the final result. They do not ask us to round. It is just simplifying only, and this is how it works. Excuse me, number 77. 2 root 6 minus 5 root 54. Now, it's unlikely that they're going to give you a problem with only two terms that cannot combine. From the onset, they cannot combine. However, 54, feeling hiccups coming along, 54 is 9 times 6, 9 being a perfect square. So, this is 5 times root 9 times root 6, which is 3 root 6. 5 times 3 is 15. So this becomes 2 root 6 minus 15 root 6. And now we have root 6's. We have like radicals. 2 minus 15 is negative 13, and we get negative 13 root 6. We're pretty good on time. Ish. I don't want to speak. I don't know what's coming up next. Number 78. I mean, it's just we've had problems that were like 40. We have sections like 40 problems long that lasted like 2.5 hours. 9 root 32 plus root 2. And once again, it's one of those things that like not only do I expect them to simplify, I'm sitting here going like, all right, somewhere I got to get a root 2 out of this, right? Otherwise, it's just a mean problem. So 9 times, root 16 times root 2. So 4 root 2. 9 times 4 root 2, which is 36 root 2. So 36 root 2 plus 1 root 2, right? That's 37 root 2. Number 79. Now it is 3 terms, so you got to kind of question what combines, if at all, or which ones, if all of them. Root 12 plus 6 root 3 plus 2 root 6. Okay, not all of them will combine because root 6 cannot simplify, and neither can root 3. But root 12 can. Square root of 12 is root 4 times root 3, which is 2 root 3. So 2 root 3 will combine with the 6 root 3. 2 root 6 will be left to its lonesome. And we are going to get 8 root 3 here, and 2 root 6 there, and happily be done. Turn the page, wash your hands, number 80. Terrible looking 80. This is where my handwriting really suffers, and I arguably it was terrible the entire time. 3 root 7 minus 5 root 14 plus 2 root 28. Cannot simplify. This can. Root 4 times root 7 is 2 root 7. So, can we do this in one step? 2 times 2 root 7 is 4 root 7. Aha. 3 root 7 plus 4 root 7 is 7 root 7. And I have a minus 5 root 14, which once again, root 14 has no perfect square factors that exist. You can bank on it. Unlike the 68, this does not have any that do exist. Cube roots. Number 81. We have the cube root of negative 81 plus 4 times the cube root of 3. 81 is not a perfect cube, but it has the perfect cube of 27. We've seen it actually a couple times now. Cube root of 27 is 3 times cube root of 3. So this is negative 3 times the cube root of 3 plus 4 times the cube root of 3. Negative 3 plus 4 is 1. You have 1 times the cube root of 3, which is also written as just the cube root of 3. And, like, listen, that is simplified, right? That's as simplified as you can get. So you might wonder why simplifying radicals is so important. I mean, you get things like this. It's nicer. Number 82. I just wrote my 8 the other way for the first time in my life. Or what did I do? I don't know. I don't know what I did. No, that was normal. How? Oh, maybe I did that. Yes. I wrote the 8 the other way for the first time in my life. The second time now. 6 times the cube root, we have variables, of 128t. The t won't get out of there. Minus 2 times the cube root of 2t. So listen, the t, I'm not saying the t doesn't matter to me, but I'm not focused. The t is just going to stay inside the cube root. I can't do anything to it. The 128, 64. 64 times 2, cube root of 64 is 4. So let's write some of this out. 4 times the cube root of, what was it, 2? 2t minus 2 times the cube root of 2t. 6 times 4 is 24. So we got 24 times the cube root of 2t minus 2 times the cube root of 2t. Okay. 24 minus 2 is 22. 22 times the cube root of 2t. Okay, we got more of the simplifying. We have multiplication. I was wondering if those were going to show up. I said, wait a minute. Why aren't they showing up in this section? Because they have their own. Simplify the expression. So we have root 2 times root 45 plus root 5. Okay, now they showed 2 different methods at the time. I've kind of spoken on these 2 different methods over and again. If I can simplify a radical early, I will. Unless I can see that it's clearly going to make a perfect square. And 2 times 45 itself is not a perfect square. So what I'm going to do is break up, or I'm going to simplify root 45 into 3 root 5. That's root 9 times root 5. And look what it actually, I didn't plan for this, but look what's going to happen. Without distributing the root 2 first, I can combine this inside 3 root 5 plus 1 root 5 to be 4 root 5. A single term, which now allows me to multiply root 2 by 4 root 5. Just root 2 times root 5 being root 10. So I get 4 root 10, which cannot simplify further. That's it. Instead of turning this into root 90 times root 10 and breaking up root 90, which actually that wouldn't have taken too long. But I make things smaller when I can if I feel like it's going to benefit my own cause, and it did. All right, number 84, we have root 3 times root 72 minus 3 root 2. And this one's already simple. Well, not simplified, but this, yeah. Root 72 is root 36 times root 2, so 6 root 2. Looks like the same thing's going to happen here. And listen, I hope not every problem does this where they can combine. I hope I can distribute sometimes, even when I'm simplifying, to just make kind of points along the way and show you different outlooks. 6 root 2 minus 3 root 2 is 3 root 2, because I do plan on simplifying earlier whenever I can. Root 3 times root 2 is root 6. You know what else I'm hoping for is that at some point when I multiply these two things that I still have to simplify the inside to say, you're still not done if what simplifies inside can go further. All right. 85. Variables. So root 5 times 2 root 6x minus root 96 x. And yes, these can still clean up on the inside. Oh, well, if they're going to keep cleaning up on the inside, then you reap what you sow. So 2 root 6x is all good. Root 96. Now the x is going to have to stay inside, but 96 is 16 times 6, and 16 being a perfect square of 4 gives 4 root 6. That x stays inside with it. I got root 6x's from both of these, for which I can combine. Root 5 is going to have to wait while I do 2 minus 4 to get negative 2. Negative 2 root 6x. Root 5 times root 6 is root 30. So I got negative 2 root 30x. 30 has no perfect square factors. We are done. Number 86. root 7y times root 27y plus 5 root 12y. Okay, I'm smelling both need to be simplified. Let's see where we go with this. Root 7y times root 27 is 9 times 3, or 20, so 3 root 3. So 3 root 3y plus 5 times root 12. So 12 is 2 root 3. So 5 times 2 is 10. So we got 10 root 3y. So both root 3y's. 3 root 3y plus 10 root 3y is 13 root 3y. Okay, here's somewhat of something that can change here. Root 7 times root 3 is root 21. So I get 13 times root 21. Now, y times y is y squared. But keep in mind, they're inside the radical. The square root of y squared is y, or root y times root y is y. This is actually going to come out. So here's an example of something that simplifies further when you're done. Root 21 couldn't, but root y squared, right, y squared could. And those do multiply. It's not a like terms thing anymore. You're actually multiplying the y's together. So that's what you get there. Sorry, my ears are plugged. Okay, number 87. Okay, you got to be careful on something like this one, where you have something squared. You have 4 root 2 minus root 98 squared. Now, I'm fully intent on simplifying the root 98 before I go any further. Oh, maybe this thing actually... Oh, okay, this thing's going to clean up. So I can show you the alternative if you really want me to. But 4 root 2 minus root 49 times root 2 is 7 root 2. So these are actually going to combine. There's still something to be careful on here. This is negative 3 root 2 quantity squared. So now when we square this, listen, you do square both parts of the product. You square negative 3, which is 9. You square root 2, which is 2. It actually does turn positive, and you get 18. I'm not going to do the alternative, but I wanted to warn you that if you do the squaring of this and don't simplify things further, guys, that a minus b squared is not a squared minus b squared. It's a squared minus 2ab plus b squared. So if you go further into this whole, I'm not going to clean this up, but if you go further into the 4 root 2 squared minus 2 times 4 root 2 times root 98 plus root 98 squared, if you do all that, I mean, that's what you have to do, and you're going to get 18 eventually. A lot of simplifying to happen. A lot of simplifying to happen. You can see where simplifying is actually benefiting us a lot. There's really no reason I shouldn't be doing the simplifying bits. Number 88, speaking of simplifying, and there's probably no ducking out of what's to come here. So we got root 3 of, when it comes to foiling, root 3 plus root 48, or maybe there totally is. Root 20 minus root 5, I take it back. I'm seeing something, yes. Root 3, root 48 has been 4 root 3 constantly here. Root 16 times root 3, and you can see those will combine. Root 20 is 2 root 5, and minus root 5, which can combine. So root 3 plus 4 root 3 is 5 root 3. 2 root 5 minus 1 root 5 is 1 root 5. And 5 root 3 times root 5 will give you 5 root 15. Root 15, no perfect squares. You're done. 2 more, they have cube roots. Number 89. We have the cube root of 3 times the... cube root of 3 times the cube root of 4 plus cube root of 32. If it's like any other problem, these should combine if I get the right recipe out. Largest perfect cube in here is 8. So 8 times 4, right? So this will become cube root of 3 times cube root of 4 plus cube root of 8 times cube root of 4. That's 2 times the cube root of 4. I got cube root of 4, 1 cube root of 4 plus 2 cube root of 4, which is 3 cube root of 4. So 3 times the cube root of 3 plus, the cube root of 3 plus 3 times the cube root of 4. Cube root of 3 times cube root of 4 is cube root of 12. So I get 3 times the cube root of 12. 12 contains no perfect cubes. It contains a perfect square, but perfect cubes are 8 and 27 and such, and this contains none of that, and that should be the answer if I did everything correct. Number 90. And yes, I prefer perfect squares over perfect cubes myself. Don't think that this isn't one step a little bit harder. It's a rarer type. And I have to write these threes all the time. Cube root of 135 minus 4 times the cube root of 5. I fully anticipate this thing to clean up. I'm guessing 5 times 27 is 135. Let's see. Yep. So why did I say 27? Because 27 is a perfect cube of 3. So cube root of 2 times cube root of 27 times cube root of 5. So 3 times the cube root of 5 minus 4 times the cube root of 5. 3 minus 4, gotta take a sip after. 3 minus 4 is negative 1. Cube root of 2 times cube root of 5 is cube root of 10, so negative cube root of 10. Water sip. Yeah, all right, ready? Here we go. It's funny because you don't get the in-between when I'm sipping water, and I just realize I just say water sip, and I'm right back, and I'm like, nah. When you do 90 problems, guys, you wear down a little bit. Number 91. Ooh, the circumference C of the art room in a mansion is approximated by this formula. Okay. 2 pi. It's kind of like it's like an ellipse thing. Approximate the circumference of the room. All right, we just got to substitute. So we are doing. See, I like how the word problems are like. We have a lot to say. Plug some numbers in. Okay, so C is about 2 pi times. I'm not drawing the diagram here, guys. 2 pi times the square root of. We're gonna do 20 squared plus 16 squared all over 2. I mean, I can go straight into the calculator with this if they're asking me to approximate, right? Let's see. Let's see where we're going with this. This is 400 plus 256 all over 2, which is 2 pi times square root of 656 all over 2, which is 2 pi, well, approximately 2 pi times 328. Yeah. 328 can divide by 4. What is 64? No. 320 divided by 4 is 82. 82, so that can 2 and 41. I guess that's as much as it can go. So let's see. I'm gonna turn these into approximate equal signs. So equals 2 pi times root 4. So 2 times square root of what I say, 82. So 4 pi root 82. All right, I'm going to approximate both that and root 2 pi times root 656 over 2. I want to make sure I didn't make a mistake anymore. So I'll just do this on my side, on the side here. So 2 pi times square root of 656 over 2. This early answer would have been, because 16 squared is 256, right? So 113.79. Let's see if this other one gives me the same answer. 4 pi times root 82. Yeah, same answer. Okay, so anyway, this is what's the feet? So square feet, no, feet, this is circumference. That's like an exact approximation, and it's about what did I say it was? 113.79 feet. About 114 feet. If you'll, there's the circumference. Okay, number 92 has 6 parts. Determine whether each expression represents a rational or irrational number. Justify your answer. I was going to say, if it has irrational things, it's irrational. But no, I look at one of these that actually is not. So 4 plus root 6, irrational. I mean, here's what I'm going to say about it, basically. I'm going to show you when something's rational by simplifying. If this can't simplify any further, then it's irrational. That's going to be my justification. Sound good? Part B. Root 48 over root 3. Now, it's one thing to, well, actually I can do it this way as well, so never mind. Forget what I was going to say. Root 48 is root 16 times root 3, which is 4 root 3. And 4 root 3 divided by root 3 is 4. You bet that 4 is a rational number. They don't say explain your answer, they said justify it. I'm justifying it. Part C, 8 over root 12. Root 12 is 2 root 3. We've seen it over and again, and maybe you know it at this point and totally understand why. I'm going to rationalize the denominator, but I see no reason that this will rationalize itself. As I'm not simplified here, but I've simplified my radical. Oh, by the way, 8 over 2 is 4. I can take care of that now or later. Let's see. Let's take care of it now. This is 4. Okay, times root 3 over root 3, which is 4 root 3 over 3. This is irrational. Anyway, I was going to say, rationalizing the denominator will keep or make the numerator irrational if you've simplified everything before that. I firmly believe that. I don't think there's any way that that's not true. Root 3 plus root 7 is irrational. I can't simplify any further. I'm just going to go ahead with that. It's irrational. Part E. A is a positive integer. We have root 10 minus... Well, actually, I take it back. Now that we're looking at this, maybe something changes. No, I don't take it back. A over root 10 minus root 2. We're just talking about whether the expression is rational or irrational, right? Yeah, totally. Multiply by the conjugate, root 10 plus root 2. Now, listen, I don't think I have anything to show here. I think the point I wanted to make was when you have stuff that simplify like this, you know, things can work out in its favor. If something's irrational to begin with, it won't rationalize later. I just want to show you that it won't. So this will be 8a root 10 plus a root 2. There's nothing that's going to take away, that's going to get rid of these root 10s and root 2s right here. On bottom, sure, 10 minus 2 is 8. That's fantastic. It doesn't change that it's still an irrational number. We rationalized the denominator, whereas we irrationalized the numerator. F. I keep thinking I'm going to take back what I said here when I find one of these that's going to totally change this. The difference here is, maybe I speak too soon. I want this to be rational to put my foot in my mouth. The difference is this is irrational on top, so I have no way of knowing what it actually is as a whole. But A was an integer. So A was rational, and I irrationalized it. This is already irrational. Maybe this will rationalize with it. 2b minus, oh boy, this is crazy. 2b minus root 5b squared over 2b minus root 5b squared. If this somehow rationalizes... Oh, hold on a second. Forget what? Well, hold on. Don't change that. Don't change that. Don't change that. Root b squared is b. Let's do that again. 2 plus root 5 over 2b plus b root 5. Okay. B is a common factor down here. B is a common factor. When you factor b out, you have 2 plus root 5. Now 2 plus root 5 is a common factor on top and bottom. They can divide, and you're left with 1 over b. I had something to simplify first. Rational. B is a positive integer. This is a rational number. Okay, for a different reason. I'm sure rationalizing the denominator would have gotten you there for all that stuff. Where's my... Oh, there it is. Sorry, I didn't bring it down. Okay, that was kind of fun. Simplify the expression 93 to 98. Okay, it's kind of, well, it's a potpourri of things, but now we're dealing with fifth roots, fourth roots, all this kind of stuff. Let's see where we go from here. And what kind of answers that you'd expect to hear from me versus a book versus photomath, all that stuff. Fifth root of 13 over 5x to the fifth power. So I'm going to begin by taking the fifth root of x to the fifth and splitting this up meanwhile. So I get x times the fifth root of 5. Excuse me. I need to find a perfect fifth value power. Fifth power value. I don't know a lot of my fifth powers. So 2 to the fifth is 32. 3 to the fifth is 243. 4 to the fifth is... To the fifth? 4 to the fifth is 1024. 5 to the 5th is 3,125. And I guess that's the number I need to get here. I have to rationalize this. Oh, this has a 5th root here, by the way. I have to rationalize this. I need to multiply by the thing that gets me 3125. That's 625. So the 5th root of 625 over the 5th root of 625. And I'm using my calculator for the top because I don't know what 13 times 625 is. So on bottom, you're going to get 5th root of 3,125, which is 5. So you get 5x on bottom. On the top, you get 13 times 625, which does not simplify. So 13 times 625 is 8125. So that's the 5th root of 8125. I hope I did that correct. I'm just trying to find something that works, and that looks pretty good enough for me. All right, number 94. We have the 4th root of 10 over 81. All right, this is 4th root of 10 over 4th root of 81. 4th root of 10 does not simplify. 4th root of 81 is 3. I mean, I'm done on that one. That was a lot faster than the previous problem. That's it. Number 95. A lot of these ones look a lot faster than that first one. I don't know what that first one was up with. What was up with the first one? The 4th root of 256y. The 4th root of 256 is 4. So you get 4 times the 4th root of y. It almost makes me feel like I did the first problem wrong. Because it was like, it's like, welcome. Here comes a really hard problem. And they're like, okay, we're going to ease it up a little bit on you. Number 96. Back to the 5th root. We have the 5th root. I mean, none of these other ones have you to rationalize anything. 160 times x to the 6th. Okay. Dealing with the x portion first, just in general. The 5th root of x to the 6th is x with the 5th root of x that's going to remain inside there. Let's just kind of keep those on their own separate path while I deal with the number, the 160. What were some of my numbers in my list? 32. Okay, 32 is the smallest. So 32 times 5. This is the 5th root of 32 times the 5th root of 5. And the 5th root of 32 is 2. So let's just write that. So 2 times the 5th root of 5. I don't deal with 5th roots a lot. That's why I kind of have to write these. So that's why it's all about familiarization. If I'm unfamiliar with it, it takes me a moment as well. So 2x times the 5th root of 5x. Okay. Number 97. Number 97, we have 6 times the 4th root of 9, does not simplify, minus the 5th root of 9, does not simplify, plus 3 times the 4th root of 9, does not simplify. As individual terms, they don't simplify. 4th roots of 9 can combine together. You do not combine the 5th root of 9 with the 4th root of 9 through addition of the coefficients. 6 plus 3 is 9. We will get 9 times the 4th root of 9 minus the 5th root of 9. Just like that. That's it. Number 98. We have the 5th root of 2 times the, oh, this is interesting, times the 4th root, what did I just do? That's not the first time I've done that. The 5th root of 2 times the 4th root of 7 plus the 5th root of 16. Okay. Nothing can simplify here as individual parts. We can distribute, but this is not going to be as fancy. Look, the 2 and the 7 do not multiply here. They have different radicals. And we see if there's anything I can do with it later. I'm not sure if I can. Let's just investigate. I can multiply. This part will clean up. I get the 5th root of 2 times the 4th root of 7 plus the fifth root of 2 times fifth root of 16. That's where these can become the fifth root of 32. Now the fifth root of 32 is 2. So you get, and listen, I want to speak a little bit more on this. The fifth root is 2 to the 1/5 power. The fourth root is 7 to the 1/4 power. I'm going to change these back. I just want to explain something there. Plus 2. They have different bases. There's nothing I can do with the exponents to add them or anything. I have different bases. I just want to just kind of reaffirm that and show that there's nothing there I can do. So they stay separate. Now, I've made this big stink about if you're within the same term, you write everything under one radical. That is true. Gosh, I'm trying to think if there's something I can do. If I get a common denominator, does that matter? Oh, I guess you can, because then they If I change 2, maybe I can do something. I don't think of things this way for the exponents, but let's go back to it. 2 to the 1/5 times 7 to the 1/4. I'm actually thinking out loud about this. I'm wondering what photomath would say. If I get a common denominator, and it's not so much about adding these things together, but if I turn this into, like, multiply this by 4 over 4, right? Multiply this by 5 over 5. If I turn this now into 2 to the 4/20ths and 7 to the 5/20ths, now they can be the 20th root together. So that would give me, and this is all plus 2, by the way. The plus 2 is just kind of irrelevant. It's on the side. But now I can turn this into the 20th root. Okay, yeah, maybe I can do this. The 20th root of 2 to the 4th times the 20th root of 7 to the 5th. Now, I wonder if something can simplify. Well, I probably not. No, nothing can. It's just 2s and 7s. But 2 to the 4th, now I'm going to put them all under the same hat now. 2 to the 4th is 16. 7 to the 5th, I don't know. I'm going to use this anyway. 7 to the 5th is 16,807. And those are together. So I'm going to put the 2 first. This is 2 plus the 20th root of... I'm going to make sure that this is correct. I feel really weird in spending time on this one, but this is where I pique my interest, and I want to write it as one radical. So the 20th root of 2,6,8,9,1,2. Now, what I need to do is make sure that this is equivalent to what I got initially, and then I'm going to use my phone to see if photomath gives me the same thing. I don't even know how to take a root of something on my calculator that's not a normal thing. I can raise it just to the power, I guess. Raise to the 1/20th power. And then all that plus 2. Okay, so 3.868. Let me see on the original problem if I get 3.868. You can fast forward past this. This is the last problem in the set. So 5th root of 2. That's 2 to the 1/5. 2 to the 1/5 times 7 to the 1/4. This is just plus 16 to the 1/5. Okay, what am I looking for? 3.868. They're the same. They're the same. So this is equivalent. I wonder if photomath would give this. Now, I don't think that part can simplify. There are a lot of reasons I want to say that, but I don't think that part alone can simplify. So I'm going to photomath the original problem. Now, this is why I use photomath, to see if they would agree with what I would do. It was this problem here. Give me 1 sec, and then I'm going to move on. Hey, hold on. There it is. All right, cool. So that was probably the hardest problem on there. So I'm glad I stuck with it. So yeah, you can give it the same. You can't do it through addition because and you can. They're just not going to combine. There's nothing they can do. No, you can't be. No, it's not going to be the same. It's not going to be the same inside. So I can't do it there. You can't do it with addition. The thing with multiplication you could do is you can multiply the insides together and work that out. There's nothing else that could simplify further. So there it is. Sorry if I was too low and you couldn't see anything that I wrote. I wasn't paying attention to that part of the screen. I was too invigorated with the problem. All right. Yeah, that's it. That was not done, but that's it for that problem. All right. We have a little bit more to go here where we are going to do 99 and 100. Use the table shown. Okay. I'm going to copy and paste that table. That looks kind of big. Okay. That looks really big now. Okay. 99. Copy and complete the table by A, finding each sum, and B, finding each product. Okay, so I guess I got to do this twice. I'm going to go pretty fast on this, okay? I might not have to explain any of it. I don't think I need to explain any of it, but I'm probably not going to explain any of it. All right, 2 plus, well, do I need to, do they want mixed numbers? All right, so, okay, it's only one fraction. 8 fourths plus 1 fourth is 9 fourths. 2 plus 0 is 2. 2 plus root 3 is here. 2 plus negative 3 is 2 minus root 3. 2 plus pi is here. 1 fourth plus 2. So this is, it's the same things twice. So I think I can just mirror this over here. So 9 fourths, 2 plus root 3, 2 minus root 3, and 2 plus pi. 1 fourth plus 1 fourth is 1 half. Which way should I go? I just go down and then mirror it. 1 fourth plus root 3. Why are they doing this? 1 fourth minus root 3. Maybe part B has, oh, this is part B. Oh, number 100. Maybe number 100 has something to do with this later. 1 fourth plus pi. So this does the same thing over here. So 1 fourth plus root 3. 1 fourth minus root 3. 1 fourth plus pi. 0. 0 plus these are just these numbers. So same thing, root 3, negative root 3, and pi. It seems to go faster at the end. Root 3 plus root 3 is 2 root 3. Root 3 minus root 3 is 0. Root 3 plus pi is exactly that. So 0 and root 3 plus pi. I'm going to have my kids do this problem. Negative root 3 minus root 3 is negative 2 root 3. Whoops. Negative 2 root 3. Negative root 3 plus pi is here. I should probably write pi minus root 3. That seems a little weird. But I won't. Plus pi, and then here we have 2 pi. Okay, that's the addition. Let's do the multiplication they want. Find each product. So 2 times 2 is 4. 2 times 1 fourth is 1 half. 2 times 0 is 0. We got 2 root 3, negative 2 root 3. This is probably going to be faster for me. And 2 pi. I just got to write that over here. 1 half, 0, 2 root 3, negative 2 root 3, and 2 pi. 1 fourth times 1 fourth is 1/16, and then times 0 is 0, and they got 1 fourth root 3. I wonder if I should write root 3 over 4. Whoa. 1/16, 0, root 3 over 4, negative root 3 over 4, and pi over 4. Just hard to fit fractions. I probably have my table too small. 0 times all of these are 0. Oh, I need to reflect things across. Give me 1 second. Root 3 over 4, negative root 3 over 4, pi over 4. Root 3 times root 3 is 3, times negative root 3 is negative 3. Oh my goodness. I hate how undoing kind of takes care of a lot of things. That happens a lot for me. And pi root 3. And then the same thing, negative 3 and pi root 3. Negative root 3 times negative root 3 is 3, and negative pi root 3, negative pi root 3, and pi squared. Time. Okay. Kind of hurt my hand. 100. Use your answers in exercise 99 to determine whether each statement, this is why we did this, is always, sometimes, or never true. Justify your answer. The sum of a rational number and a rational number is rational. True. I don't want to justify it. Guys, I'm not going to justify them. Well, unless I feel a need to. A. I'm not going to type it out. True. Rational plus a rational is rational. B. The sum of a rational and an irrational is irrational. True. even in the case of 0. 0 plus root 3 is still root 3, or 0 plus pi is still pi. Root 3 plus root 3 is still 2 root 3. Oh, I'm sorry. This is always, sometimes, never. These were always. Always and always. You know what? I'm going to type this. Always, always. C. The sum of an irrational number. Wait, didn't we just say this? Oh, no. Wait. Yeah. Oh. I might have mentioned... No, that's good. The sum of an irrational and an irrational is irrational. I think I mentioned that for the last one. I think I said root 3 plus root 3 is 2 root 3. That's also always true. Unless I'm missing something, that should work out. Products are a different story, and this is what they're talking about next. Product of a rational and irrational is rational. That's still always true. That's still always true. The product of a non-zero... you're getting at me. Non-zero rational number and an irrational number is irrational. I believe that's also always true. Now, let's make sure... Rational and an irrational, non-zero. So 0 is going to give you 0, right? But 3, yeah. And F, the product of an irrational and irrational is irrational. That's not always true. That's sometimes. So in this case, I'm going to justify the sometimes because I want to look at those examples. I can show one that counters that. So when you have root 3, let's see. I'll write this part out. When you have root 3 times root 3, that gives you 3. Whereas root 3 times pi is pi root 3. So rational, irrational. I hope I did this right. That's a bunch of alwayses, and there's no nevers with a sometimes at the very end. That seems to kind of work out in my head. I guess that's the point of the table, but it makes you think about different things. It's weird that they had 0 before, though, because I was like, I wanted to use 0 to make that point of the other part. All right, 101, reasoning. Let m be a positive integer. For what values of m will the simplified form of the expression square root of 2 to the m contain a radical? For what values will it not contain a radical? Explain. Okay. Positive. So we're not dealing with negatives. That's good, because I was going to talk about negatives with it. So root 2 to the m. If m is odd, it will contain a radical. It will have a radical. Okay. If m is an odd number, that's not true at all. Not for 2. Hold on a second. Positive integer. I was thinking of x. 2 is different. 2 to the first. Okay, 2 squared, 2 cubed. Yes, no, I'm not. Yes, no, we're good. If m is odd, it will have a radical. Square root of 2 to the first is square root of 2, which is good. Square root of 2 cubed is square root of 2 to the 8th. I was thinking of cube root, which is 2 root 2 and such. So if it's odd, it'll have a radical. If m is even, it will not have a radical. They keep saying explain. My explanation is going to be a little bit easier than what I was just saying as examples. I was telling you what like 2 to the 5th is and stuff like that. Think of it like a variable. Think of it like the square root of x squared, the square root of x cubed, the square root of x to the 4th. You're dividing your exponent by 2. 3 divided by 2, 4 divided by 2, 2 divided by 2. If it can divide by 2, then everything comes out with the base. If you divide an odd by 2, there's a remainder. So odd powers will contain a remainder when dividing by 2. Sorry about the handwriting. By 2. It's kind of near the end here. All right, that was 101. They make us think. What they say? Was it critical thinking? Oh, reasoning. 102. The edge length s of a cube is an irrational number. The surface area is an irrational number. and the volume is a rational number. Give a possible value of S. Okay, surface area of a cube, so 102. All right, so volume of a cube is S cubed. Surface area of a cube is there's 6 faces with S squared on them. So we want the volume to be rational, and we want the surface area to remain irrational. So when we cube something, it rationalizes. Prior to that, it's not. So we want S to be a cube root of something. So for example, let's say want S to equal cube root of something. So let's try something like 4, cube root of 4. If S equals cube root of 4, then that's irrational. The surface area is the cube root is 6 times the cube root of 4 squared, which is 6 times the cube root of 16. I can simplify a part of that. Cube root of 8 is 2, so that's 12. 2 root 2. 12 times the cube root of 2, which is irrational. But volume would be cube root of 4 cubed, which is 4. Whoops. Which is 4. Which is rational. So cube root of 4 works for me. Cube root of 4. Or cube root of anything that's not a perfect cube already. And I don't know if they wanted units like inches or whatever, but that works. 103, another reasoning question. Of course. Let A and B be positive numbers. They're really making me think here. Let A and B be positive numbers. Explain why the square root of A times B lies between A and B on a number line. Hint, let A be less than B and multiply each side of A is less than B by A. Then let A is less than B and multiply each side by B. Okay? So if we say let A less than B, let's multiply both sides by A. I don't know if I would have thought about this on my own, and I don't know how much they're leading me. A squared is less than AB. If we take the square root of both sides, given that they're positive, there's no plus or minus here, A is going to be less than the square root of AB. Now, when we let A be less than B, let's multiply. Actually, I would have thought of this over time. Multiply both sides by B, we get AB being less than B squared. If we take the square root of both sides, with these being positive, we're going to say the square root of AB is less than B. Therefore, with these things together, we can conclude that the square root of AB is between A and B. Okay, cool. That's it. Just A, it lies between it. All right, making an argument, 104. Your friend says you can rationalize the denominator of the expression 2 over 4 plus cube root of 5 by multiplying the numerator and denominator by 4 minus cube root of 5. Is your friend correct? Explain. Your friend's not correct, and I think this is something I was mentioning. I forget if it was in the lecture portion or just doing some problems and saying, I wondered where rationalizing does occur on these things, like if you have to do it more than once or something like that. So I'm just going to say it straight up. Your friend is incorrect. Your friend is incorrect. You will end up with 4 squared minus root 5 squared. So 16 minus, I'm going to leave some room and just write that out. You'll end up with 16 minus the cube root of 25. Not the square root of 25, the cube root of 25, which is not rational. Which is not a rational value. Now, curiosity comes into play. Of course, you can rationalize this eventually. If you do that, Now what you do is now you multiply top and bottom by 16. I don't know. You could probably factor out. If I do 16 plus that, 5, that's not, I don't know. I don't know if it eventually rationalizes. I don't do it with those. I do them with square roots, right? So anyway, no, that's not rational. It doesn't rationalize. Water. Brr, I feel flushed. All right. Number 105. Problem solving. The ratio of consecutive terms in the Fibonacci sequence gets closer and closer to the golden ratio as n increases. I didn't know that. Find the term that precedes 610 in the sequence. Okay. I don't know if I'm supposed to do something specifically with that. I guess I just use it within there. So let's try that. 1 plus root 5. I guess it should be pretty close to it. 1 plus root 5 over 2 equals, so the one that precedes 610. 610 would be the bigger one, and the unknown would be x. Let's see how close it is to some value, because it says it gets closer and closer. This must be large enough that when we approximate this, I'm not even going to simplify it. I'm going to just calculate it. Use the calculator. So we cross multiply, all that kind of stuff. So we're going to get x times 1 plus root 5 over 2. Because it doesn't make sense to do the simplification part. That part doesn't apply to what I need, right? It doesn't divide by anything anymore. This equals 2 times 610, which is 1220. So x is going to be 1220 over 1 plus root 5. So I'm going to use my calculator for that. I'm going to do 1220 over 1 plus root 5. So we're going to get 1220 over 1 plus root 5. So 377.0. Okay, so 377. Which kind of shows that that's what that number is that precedes it. If you guys don't know what the Fibonacci sequence is, it's this list here. And I don't know if it starts with 0 or not. I don't know if that matters. But you add the two numbers before this. 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3 is 5. 3 plus 5 is 8. 5 plus 8 is 13. I like the question, though. And I was thinking, it was funny, because I was actually thinking of Fibonacci sequence when I was explaining the golden rectangle, golden ratio. 8 plus 13 is 21. So I could have kept doing this until I got to 610, but 377 must be in the list. It's got all congested, sorry. All right, number 106, all right, two more. Use the golden ratio, 1 plus root 5 over 2, and the golden ratio conjugate, 1 minus root 5 over 2, for each of the following. Show the golden ratio and golden ratio conjugate are both solutions of x squared minus x minus 1 equals 0. Now, you guys don't yet know how to solve non-factorable. You have not yet knowing how to solve non-factorable things using other means. So I'm just going to substitute into here. So let's try it. Let's try 1 plus root 5 over 2. 1 plus root 5 over 2 squared minus 1 plus root 5 over 2 minus 1 equals 0. Let's see if it does. All right, the over 2's are squared to get 4, right? So 4, or that one is 1 plus root 5 squared is 1 squared plus double this product of 1 times root 5 plus root 5 squared. So we have that. I have 1 plus root 5 over 2 here, and I have a negative 1. I might need to use the other page for this. Let me copy and paste this over. I like to use the lines, even if it's kind of messy. It's probably the worst argument to say I like to use the lines, because I'm writing what I'm writing right here. Okay, so I have that. Now 1 plus 5 is 6. So I got 6 plus 2 root 5 over 4 minus, now I'm going to get common denominators here. Let's multiply everything by 4. Let's do that. Let's do everything times 4. And now that 6, 1 plus 5 is 6. All that stuff, I just got 6 plus 2 root 5. Now over 4 is no longer there. Now when I make this thing times 4, 4 divided by 2 is 2. 2 times 1 is 2. 2 plus 2 root 5. And then 1 times 4 is 4. Okay, made everything 4 times bigger. I like that. Now, is that true? You know, generally they don't like us to do that. Move things to the other side of the equation like that. So maybe I should have kept the fraction. But I'm working here. So 6 plus 2 root 5 minus, notice I have to distribute that. Minus 2 root 5 minus 4 equals 0. 2 root 5 minus 2 root 5 is gone. 6 minus 2 minus 4 is 0. So 0 equals 0. That checks out. Okay, I got to do the same thing for the other one. I imagine I can just use some of the values here and just change their signs up because everything else will be the same. So I get 1 minus 2 root, I get 1 minus root 5 over 2 quantity squared. So that was the first one. Here comes the second one. 1 minus root 5 over 2 quantity squared minus 1 minus root 5 over 2 minus 1 equals 0. When I square this, I'm going to now get this. I mean, it's the same stuff as before. 1 minus 2 root 5 plus 5, though, this time. And then here, on this one, when I subtract, this will be 1 minus root 5 over 2. So when we distribute, whether I multiply by 4, whatever it is, it's just going to look the same. So times 4 here, the only difference is this is minus 2 root 5, and this is going to be plus because we got to distribute the negative. So now it's going to become, ultimately, 6 minus 2 root 5 minus 2. Oh, because the 1 plus 5 is 6. Minus 2 plus 2 root 5, because that distributes, the negative distributes into these. Remember, it's 4 times that. Minus 4 equals 0. And the same thing happens. Negative 2 root 5 plus 2 root 5 is 0. 6 minus 2 minus 4 is 0. So 0 equals 0. And that checks out. Okay. That was part A. Part B. Construct a geometric diagram that has the golden ratio as the length of part of that diagram. If they're talking about what I was showing you before, construct a geometric diagram that has the golden ratio as the length. I don't even know what they want me to do. Boom. I mean, I literally don't know what they want me to do. I don't know what they want me to do. It's 1 plus root 5 and 2. I'm not sure what they want me to do. There it is. I have no idea. I'm actually stumped for a question. I hope I did it right. All right, number 107, last question. I mean, I showed you what the golden ratio thing was before. Hopefully you can live off that for a bit. Use the special product pattern A plus, sum of two cubes. Use the special product pattern A plus B times A squared minus AB plus B squared equals A cubed plus B cubed to simplify the expression 2 over cube root of x plus 1. Explain your reasoning. Oh, that's how you multiply. Oh. Okay. So 2 over cube root of x plus 1. Consider this to be your. I should have thought. Why didn't I think of it? See, I'm not the best math teacher in the world. Anyway, so this is like your A plus B right here. This is your A. This is your B. If you want to get this thing canceled, you don't multiply by a conjugate. In that form, you multiply by something to get, instead of a difference of 2 squares, but a sum or difference of 2 cubes. And this thing, we can multiply top and bottom by, yes, the cube root of x squared, the cube root of x squared minus 1 times the cube root of x, so minus cube root of x, plus 1 squared over this. Yes, sum of 2 cubes. That's you'll learn that in IM3. It's just that you don't learn it for this reason. I don't know why I didn't think about this. Any other teacher that I asked would have said, "Oh, use the sum of 2 cubes." And duh. Sorry, it's something a math teacher should have known. I'm sorry about that. Anyway, this bottom, I know this looks confusing. You know what the bottom becomes? It becomes this cubed plus this cubed. You know what this cube root of x cubed is? X. You know what 1 cubed is? 1. It becomes x plus 1. The top's going to look weird. I promise this won't look more simplified. I got to finish. Promise this won't look more simplified than what it was before. But 2 is going to distribute in here. And that works. That's your simplified answer. It's not beautiful, but it does work. All right, guys, that'll do it for this one. I'm trying to talk about hiccuping again. This Mr. Robinson, thank you so much for watching. Take care. I will see you in the next one.